What if the foundations of reality, everything that we see around us, is not quite what it seems? From the very smallest scales to the very largest, physics starts to break down. Black holes, quantum mechanics, the three dimensions that we see around us. In this video, we're going to see how all of these topics, when you peer down deep into them, they start to unravel. In this first video, we're going to look at how physicists use the fourth dimension. Unlike the three dimensions that we see around us, this fourth dimension can help explain quantum mechanical effects and probe the very fundamentals of reality. But what would this fourth dimension look like?
The fourth dimension. For a long time now, the idea of a fourth dimension has hovered at the edge of science and science fiction, a concept so elusive and mysterious that many of us find it almost impossible to comprehend. But could an additional layer of spatial reality truly exist, hidden beyond our three-dimensional worldview? Maybe, just maybe, the fourth dimension is more than a sci-fi buzzword. Tantalizingly, scientists now claim to have built a fourth dimension of space, and in this video, we're going to peer inside and explore this new reality, and explain just what a four-dimensional world might look like. We experience the world as three dimensions of space and one of time, with time normally being referred to as the fourth dimension. But forget what you have learned. Today, we're going to explore an even more abstract idea. Can we build a fourth dimension of space? And what strange properties might it contain? Mathematically, at least, we can easily conceive of worlds that contain 4, 6, even 100 spatial dimensions. In fact, branches of theoretical physics, such as brane cosmology, already suggest the existence of many spatial dimensions. Remember the movie Interstellar? Now, spoiler alert here for anyone who still needs that. The wormhole that brings the crew to Gargantua moves through a hyperspace known as bulk space, which is a higher spatial dimension, and it's what allows the ship to emerge at a new non-linear location. And leaning on that other mainstay of sci-fi movies, the Marvel Cinematic Universe, the term tesseract describes a mystical and powerful cube that possesses a space stone, a device that has the ability to open portals to any location in the universe. Again, it does this by accessing a higher spatial dimension similar to Interstellar's bulk space. But the term tesseract, well, that's borrowed from mathematics, where the word describes a four-dimensional cube, also known as a hypercube. But outside the realm of sci-fi, how can we possibly conceive of something that exists in a fourth dimension? In recent years, a new generation of quantum physicists have turned that abstract question into something surprisingly concrete. Instead of searching for hidden dimensions out there, they have started to engineer extra dimensions in here. Well, in quantum labs, to be precise. It has profound implications for our understanding of reality, and it may drive quantum technological innovation well into the future, just as soon as we can grasp it. To better understand what it all means, we're first going to have to get our heads around dimensions. So up, down, left, right, forward, and back. We assume that that's all there is because that's all we can see and touch. And it may be, though, that our limited senses are constraining our understanding of reality. Imagine being born into a room with no windows. How would you ever conceive of the world beyond your immediate environment? In the 19th century British novel Flatland, the characters are all two-dimensional shapes living on an infinite sheet of paper. Our narrator, a square shape, helpfully named A Square, can move left, right, forward, and back. But he has no concept of up. When a sphere from a three-dimensional world passes through Flatland, A Square never sees the sphere. Instead, he only sees the parts that interact with the 2D world. At first he sees a point, then a growing circle, then a shrinking circle, and finally nothing at all. To our character, the sphere only manifests on two-dimensional planes as a series of mysterious two-dimensional slices that change over time. The story perfectly demonstrates the bewilderment many of us feel in trying to wrap our heads around a world beyond 3 dimensions. Now, if there were a 4th spatial dimension, we could never see a 4D object from the outside. But that doesn't mean that we can't explore this strange idea, and in doing so, learn more about our perception of reality.
Yeah, so I think the best way to think about 4 dimensions is by building an analogy with the number of dimensions that we're used to, and then trying to extrapolate it.
That's Hannah Price, a theoretical quantum physicist at the University of Birmingham. When physicists like Price talk about a 4th spatial dimension, they mean something specific, an extra independent direction in which things can move. On a flat sheet of paper, there are 2 directions, x and y. In everyday space, there are 3, x, y, and z. Add a 4th spatial dimension, and it would simply be another direction, perpendicular to all the others. We could call it q. If a square in Flatland discovered a new dimension, it would mean a new freedom of movement. And that is really exciting for physics.
And that freedom is actually really crucial when it comes to physics, because it changes the way that a lot of physical laws behave. So it changes the way that gravity would work or electromagnetism would work. And the aspect that I'm really interested in is it would change the way that certain types of quantum materials would behave. Just by adding that extra direction in which your particles can move, you can realize different states of matter that you wouldn't otherwise see in the kind of the universe that we have with 3 dimensions.
In other words, higher dimensional physics acts like a blueprint, constructing a reality of which we can only perceive a part thereof. But this is where it gets exciting. By imagining our reality as in the shadow of something higher, we might be able to glimpse at this untapped, unique physics of a 4D world.
It's like the higher dimensional system is casting a shadow into the lower dimensions that exhibits many of the same features and same properties. And so by looking at that kind of the shadow of the effect, we're inferring things about the effect that would exist in higher dimensions as well.
Price is part of a new generation of scientists who believe it is possible not only to theorize about a 4th dimension, but to actively explore it through tangible experiments. The question is how? While there is no way we can physically see a 4th dimension, that doesn't mean we can't simulate its effects on our 3-dimensional space. And the answer lies in a curious discovery from the early 1980s, known as the quantum Hall effect. In the 80s, German physicist Klaus von Klitzing was working with atomically thin layers of very cold semiconductors, effectively creating a 2-dimensional sheet of electrons. When placed in strong magnetic fields, the electrons started moving in ways that challenge our understanding of the physical world, as if slipping through a sort of secret passageway, or, more to the point, a hidden coordinate beyond what was available to them. Von Klitzing later won a Nobel Prize in physics for his quantum Hall findings. So what was going on? In these systems, the electrons were confined so tightly that they were only free to move in 2 directions, a bit like our friend in Flatland. But this is where it gets strange and a bit complicated, so stick with me. If you apply a magnetic field to this atomically thin 2-dimensional electron wafer, it makes all the electrons inside it want to move in tiny circles, except at the edges where there isn't enough space. Here, the electrons' trajectories are chopped off into semicircles. But instead of stopping in their tracks, these electrons zip along the edge, forming a conducting periphery. This is called the quantum Hall effect, and it creates a material that is electrically insulating in the middle, but conducting on the sides. This unusual duality depends on the 1-dimensional edge using the presence of a higher dimension that it wasn't expected to have access to. To understand how this works, imagine a 1-dimensional line with electrons sitting on it. If you apply a magnetic field to this, the electrons can't move in circles, as that isn't possible in one dimension. So they remain fixed in place. If this line is the edge of a wafer, however, the electrons can skip through the two-dimensional plane.
Your particle is trying to move in a circle, but it keeps hitting the boundary before it's managed to go all of the way around. And every time it hits the boundary, it reflects off and it comes back in the same direction it originally started. And then it does another little circle. And this leads to what we call a skipping orbit.
In short, the electron is skipping between the exterior one-dimensional edge and the interior insulating bulk via a second dimension. The quantum Hall effect is the simplest example of what's called a topological material, a system whose behavior at the edges doesn't depend on tiny details of the material, it depends on a deeper mathematical structure underneath. And that raised an intriguing question. If a one-dimensional line can pull neat tricks when it feels the imprint of another dimension, can higher dimensions do the same? Theoretically, yes. In 2001, Xu Chengzhang and his colleague Xiangping Hu, then both at Stanford University in California, developed the mathematics that described a four-dimensional analog of the quantum Hall effect, one in which a regular three-dimensional material felt the imprint of a fourth dimension. And this idea intrigued Price.
There had been the prediction in the early 2000s of the 4D quantum Hall effect, which generalized the 2D results. And that was what really took our imagination, and we thought, okay, let's try and figure out how to realize this experimentally.
The question now was how? To create their first 4D simulation, Price and others created a lattice of atoms held in place by lasers. By tweaking the lasers, they could deform the lattice to generate the ghostly shimmer of a four-dimensional object. It was a real-world example of what a square had experienced with the sphere in Flatland. And together with a separate experiment published at the same time, it was the first realization of the quantum Hall effect in 4 dimensions. But it's hard to say what or where the 4th dimension is in these experiments. It wasn't 4D enough. Far better than conjuring the impression of a 4th dimension is actually building one, which is where we're going next. When it comes to accessing multiple dimensions, there's no better place to look than New Scientist. Our company was founded in 1956 for all those interested in scientific discovery and its social consequences. And we love to ask the big picture questions about life, the universe, and what it means to be human. If that sounds like something you like too, then why not join us? With the New Scientist digital subscription, you'll get access to all of our award-winning science and technology journalism, including our daily news so you're up to date with the latest developments, and our deep dive features so you're never without a captivating tale to fuel your curiosity. For a great offer on a New Scientist digital subscription, click the link in the description. So, let's build a 4th dimension. Price wanted to know if anything like it could be built in the lab. The first step was to design a model that captured the essential 4D physics in a form that experimentalists could work with. Enter Chong Yedong, a quantum researcher at Nanyang Technological University in Singapore, who, utilizing Price's theories, constructed the world's first permanent 4D electrical circuit.
So from a very pragmatic, practical sense of point of view, if our goal is to, for the first time, create a physical structure that is equivalent to a 4-dimensional lattice, making use of Hannah's principle, her model as the guiding principle, then electrical circuits are the way to go. But the advantage of using electronics is really that you can hook up different electric resonators with a wire, which means that I can take this 4-dimensional structure and I can peel it out into layers and lay it out into a 3-dimensional stack of circuit boards. If you have a 4-dimensional material, you can have a generalization of the quantum Hall effect.
To understand how it works, picture a three-dimensional object, say a cube. If we look at this, we can see how the lines, which can be considered one-dimensional objects, are drawn to connect elements of the shape. Now, if we unfold that cube into 2 dimensions, we get 6 squares, all spread out. Now, in 3 dimensions, we know that the edges of these squares were all next to each other, but in 2 dimensions, they're not. If we made a circuit board of this shape, we could wire it so that each edge acted like it was next to its 3D neighbor. Essentially, this is what Chang's group did. Visually, it looks like a dense, multi-layered motherboard, but mathematically, it is a 4-dimensional grid. So if this circuit really behaves like a 4D quantum Hall material, how do you tell? In the 2D effect, the bulk was the insulator and the edge was the conductor acting in a special one-way state. The 4D version predicts something similar, special states that live on the 3D surface of the 4D lattice.
The whole idea behind using the electrical circuit to simulate this was to really exploit the fact that an electrical circuit you can wire up however you like. And so this means that if you want to wire it so that there are 4 directions in which the current can flow, you just need to attach 4 wires to the node of your current.
In other words, Price and Chang's teams created a 3-dimensional electrical circuit whose behavior matches the equations of a 4-dimensional quantum Hall material. Within its network of capacitors and inductors, there is an extra effective direction along which waves can propagate, a synthetic 4th dimension.
We were looking to show that this 4D circuit exhibited characteristics that we would expect from the 4D quantum Hall effect. And indeed, they were able to show that. So they were able to verify the existence of those 4-dimensional surface states. And this was what I think the first experiment that was really a 4-dimensional experiment looking at this effect, because the connectivity was 4-dimensional.
Now that there was a mechanism for simulating a 4D environment, things could get really fun. By building on the basic blueprints by which Xi and Chang Yidong conducted their experiments, one could, they say, easily manifest the quantum Hall effect in 6 dimensions. Theorist Motohiko Ezawa at the University of Tokyo goes even further, saying that the kinds of electrical circuits engineered by Yidong's group have the potential to manifest as many dimensions as experimenters have the patience to wire up. All of this, however, doesn't quite prove that the universe is 4-dimensional. Price herself is ambivalent to the idea, but like all good scientists, is open to discovery.
I don't know whether there are more than 3 spatial dimensions in reality. I'm not a string theorist, so I am agnostic as to whether, in fact, there are more spatial dimensions than the 3 that we experience. But I've really long been fascinated by the question of what would happen if there were. So for me, this is an exercise of the imagination and creativity.
What it does mean is that we have learned how to engineer systems that act as if they are 4-dimensional. The circuit has 4D connectivity, but it still lives physically in ordinary 3-dimensional space. Shinsei Ryu, a professor at Princeton, notes that each of the aforementioned experiments was conducted with a guided hand within synthetic environments. Any seeming 4th-dimensional activity was, in a literal sense, entirely of human creation. He also notes that the experiments don't account for the electrons' behaviors, such as mutual repulsion that results from their charge, which is still governed by the 3 normal dimensions. Now, Hannah herself agrees. It is as yet impossible to see and measure to what extent these particles utilize 4D, quote-unquote, hidden tunnels under natural and unmanipulated circumstances.
I completely agree, and I don't think the electrical circuit was ever intended as a be-all and end-all. So his concern is completely accurate. There are other ways of getting these extra dimensions which are much more faithful to properties that you would expect from a dimension, and that are much more likely to have this sense of like the right kinds of interactions.
A lot of the physics that we are interested in for this so-called dimension hopping don't have anything to do with particle interactions at all. Now, there's a whole other branch of materials physics that have to do with interacting materials and how do you define topological materials when interactions are not merely present but strong. That is a subject of interest in itself. These things actually have real-world possible technological applications.
Already other groups are taking on the mantle. A 4D quantum Hall experiment in Paris, for example, has been able to observe the motion of a particle in a 4D environment, opening the door to understanding the fine structure of these dimensions and studying interacting physics. And this is one of the really exciting futures for Price, Yadong, and others' higher dimensional research. Not only do we expand our physical knowledge about the nature of reality, possibly even proving the existence of a fourth or more dimensions, but it also has real-world technological impacts too.
There's a very common misconception that quantum physics is only relevant for studying microscopic objects, or really the properties of atoms, and doesn't really affect our daily lives. The normal computers that you are, watching this video on, for example, are powered by the laws of quantum mechanics.
Like all topological states, these materials have useful characteristics. It turns out that any impurities on the surface won't impede an electron's progress because it can always skip through a higher dimension. This makes them good electrical conductors. In the future, these exotic properties may not only accelerate current technology, but also power the next generation of super-fast quantum computers and beyond.
What I would hope is that some of these really fundamental questions that we've been asking about higher dimensions translates into, okay, this is an alternative way to come up with cool devices, to come up with cool ideas for controlling light and particles in the future.
And this, in the end, might be the most exciting part. Space portals and all-powerful mystical objects like Marvel's Tesseract or Interstellar's wormholes will likely remain relegated to the realm of science fiction. But here in the real world, as we embrace and explore a new and potentially more exotic understanding of our universe, the only limit is our ability to open our minds, to imagine, and to innovate. Could we be living in our own flatland? Well, now we may have the tools to answer that question.
We've seen how reality might be more complex than the three-dimensional world that we're familiar with. But what if reality is much stranger? What if space and time and even particles don't exist? What if we need to come up with a completely new framework to understand reality? In this next video, we're going to see physicist Vlatko Vedral talk about his radical new theory of reality.
In general relativity or in quantum mechanics, apparent contradictions are a consequence of this wrong view of reality, that there is a classical world out there.
According to you, particles, space, and even time don't really exist.
The ultimate elements of reality are the Q numbers and not necessarily the existence or non-existence of an atom. That's a mind-blowing conclusion, that actually not just particles of light, which are massless like photons, but even bits of matter could actually be created, destroyed. They could exist in this superposition of being created and not created simultaneously. There is a deeper underlying reality which cannot be created and destroyed.
I don't know if I dare open this can of worms, but what about time?
That's also mind-blowing.
Vlatko, thank you for joining us today. Really appreciate it. You've written this book, which is called Portals to a New Reality. And it's really kind of about your vision for the future of physics, isn't it? And
Yes.
I've been having a look, and there's some bold stuff in there. You say that this is the list of things that, according to you, don't really exist. Particles, space, and even time. So we're going to kind of dig into that and unpack what you mean by that.
Yes.
I want to start, if it's okay with you, by just talking a little bit about what it means to be a theoretical physicist these days, because some people would have this sort of antiquated idea of you just sort of in a room and writing equations, but is there any truth in that? What are you actually trying to discover, and why do you do what you do?
Yes, I think the question that drives me really, usually the questions are of very fundamental nature, but you have to use your intuition there as to what you think might be a fundamental question that would really change how we think about the basic laws of physics. These are the fundamental questions. You never know in advance, of course, which question might turn out, but you will have an intuition. So going into the areas where you are unifying quantum mechanics and general relativity, are two best theories which haven't been unified. Usually questions related to that are considered fundamental and really likely to give us new physics. Whereas, of course, there are many other questions where you are applying general relativity and quantum mechanics, and they are interesting, but they are maybe not interesting for the fundamental purpose.
So I guess you're trying to, I don't want to put words in your mouth, but you're trying to see deeper into the kind of the essence, the base layers of reality. Is that right?
Yes, that's right. You're trying to determine what you think are the fundamental constituents of reality, and then immediately how that impacts our theories and how could one test whether this really is the right way to proceed.
Yeah. Take something like general relativity. It's more than 100 years old now, isn't it? And it's kind of our description of space and time. Einstein, of course, came up with it. So in a sense, you might say that we understand space and time, but you're looking for chinks in the armor, gaps where our understanding fails a little bit. Is that so? Maybe give us an example.
Yes, I think that's right. I think that's why you require a certain intuition to approach this, because of course, there is no formal mathematical procedure how to come up with these questions. And actually, as you do come up with them, they may lead you astray. Maybe they are not the right questions to ask, and they turn out to be completely tractable and trivial. So indeed, for instance, if you take general relativity, people observe all sorts of anomalies out there in astrophysics. So when they are looking at motions of galaxies, or when they're looking at black holes and the sizes of black holes, very frequently, one possible interpretation for the deviation is that something might be wrong with general relativity. And that could be the right intuition. Of course, what can also happen is that your observations are not detailed enough. And if you were to do further observations, you would just realize that it's not exactly what you concluded previously, or maybe there are other objects that you missed out in the previous observations, which are the ones that make it appear to be deviating from general relativity. However, if you take them into account, you get no deviation. And I think this exists in both of our fundamental theories, in quantum mechanics as well as in general relativity.
Before we get into talking about that in detail, I wonder if you can just kind of give us a bit of a basic guide to kind of what, because physics kind of has these two central pillars, doesn't it? It's got general relativity, our description of space and time, and then it's got quantum mechanics or quantum physics, our description of the microscopic world of particles and interactions. So we're going to kind of break those down a bit in this conversation, and we're going to see where you think the flaws are. But just give us the outline of how we think those two things work in the mainstream at the moment.
Yes, I think they came up, quantum physics and general relativity really came up from two completely different domains, the micro, quantum mechanics, and the macro domain, general relativity. And so the problems that led to the creation and the discovery of these two theories were completely different problems. They had no overlap whatsoever. One set of problems involved in general relativity things like motion of planets. Are there deviations from Newton's laws in these motions? Bending of light was another very big question. How much does light bend when it passes by a massive object? And there was a prediction due to Newton, and there was a different prediction due to Einstein. And none of these problems had to involve any quantum mechanics. In fact, quantum mechanics, if it's relevant at all, the effects are so tiny that we are not really able to measure them at all at present. Quantum mechanics, on the other hand, came from atomic physics. People were struggling to understand spectra. When you shine some light on an atom, and the atom answers basically by shining light back, and you detect that, the question is, why do these colors come in a discrete set of frequencies? Why not the full continuum? And that led various people, of course, Max Planck first, then Einstein himself made a fundamental contribution, then Niels Bohr ultimately accounted for atomic spectra in his own model, and that this ultimately led to the birth of proper quantum mechanics. So these were problems where gravity was completely irrelevant. These are tiny objects. The gravitational forces between objects like that even now cannot be measured, actually. They're too small to give you a measurable effect. So you know that you can ignore gravity completely. And if you then fast forward over the last 100 years, both theories have been confirmed. That there's not a single deviation either in general relativity really or in quantum mechanics in any experiment that we've done. But it's still true that none of these experiments probe the common ground between the two theories. So they're really, they have a separate existence, and both are equally valid, if you like, in terms of experiments.
They kind of do different jobs, don't they?
They do completely different jobs.
Yeah.
Yes.
So I guess like the way, maybe you can tell me if I'm getting any of this wrong, but as a journalist, you know, I think of general relativity as kind of, it paints space-time as this kind of flexible canvas.
Yes.
It bends, and it's that bending of space-time that creates, if you like, gravity, or just is gravity.
That's it.
And then you've got quantum theory, which is talking about kind of the energy in and out from particles, the interactions of particles and light. And I guess for me, the fundamental point about it is that like the energy levels of particles, we think of them as these fundamental ingredients of reality. And the idea is that they can absorb and release energy in packets. It's not like a continuous thing. It's like they can, little blip comes out then another little blip comes out.
That's it.
I'm obviously dumbing it down.
Yes, yes.
But that's more or less...
that's it,
right?
That's exactly right. So in many ways, general relativity is still a classical theory according to this logic, because everything is continuous in general relativity. Space and time are continuous numbers, whereas in quantum mechanics, everything somehow becomes discretized ultimately. And I think the first discovery was exactly as you said, that energy only comes in little chunks, the quanta of energy. So both of these theories, they really arose from a completely different set of problems. And the frustrating thing to some degree is that they still continue to exist in exactly the same way.
So I promise we're going to come to your ideas, Vlatko. I think the last thing that we kind of need to set up, because we're going to go on to talk a bit about observers, which has this very particular meaning in physics, doesn't it?
Yes.
Just tell me a bit about what it means in quantum mechanics to talk about an observer. I know you think that it's a bit of a misleading term, but
yes, it's a great point to start, because people frequently say that the trouble with quantum mechanics is that, so the argument would go, is that it requires the existence of observers. So there has to be an ultimate kind of frontier where you detect quantum outcomes. And the people who argue this way would say it's only at that point that things become real. And this is because in quantum mechanics, things can exist in a superposition of many different states. So you can have an atom that exists in two spatial locations at the same time. And quantum mechanics says this state will persist until you somehow engage with this state.
You look at it.
You look at it in some way. Of course, you would involve a lot of experimental apparatus to do that. It would be through some kind of optics elements and things like that, you would amplify it to your computer screen. However, it is as simple as looking at it. And then the question is, you only get one of the two outcomes. And that's what quantum mechanics tells us, that you cannot predict. There's no algorithm to predict which of the two outcomes you will get. It's a random, it's the most random process that we are aware of in the universe. However, beyond that point, the observation solidifies this outcome and you get one of the two outcomes. And some people would say, before you made the measurement, this property of being here or there was not real, it wasn't actual, but you need to ask this question, you need to look at the system to really find out whether it's in one state or another. And
it leads to all these metaphysical questions, doesn't it? Because if you've got a theory which says before you look at something, it's in two places at once. Maybe the most successful theory in science, and maybe some people would say it is, but what does that really mean? What constitutes an observer? And that ties people up in knots a bit.
Yes, it does, and I think we've been arguing about it right from the conception of quantum mechanics. I think there was a famous 1927 Solvay conference in Belgium, and basically this was a conference that involved all of the pioneers of quantum mechanics. Certainly Einstein was there, Niels Bohr was there, Heisenberg, Schrödinger, Dirac, all of these people were there. And in fact, they couldn't agree on how to think about these things. What does it mean to observe something? Why is the behavior different if you were to observe something than if you didn't observe the system? And again, this is a big departure, people argued, from classical mechanics, where a particle has a position and a speed independently of whether you look at it or not. So you can detect someone's speed of motion without really slowing them down or speeding them up. In classical mechanics, there is no back action, if you like, no knock-on effect there. Whereas in quantum mechanics, you can never avoid that. And that's the key to Heisenberg's uncertainty principle as well. And then various interpretations, in fact, were offered already in 1927. You can see 3 or 4 key different camps into which researchers fell into, and basically there were the camps that I think maintained the relevance of observers to a different degree. What exactly constitutes an observer? That's the key question.
So let's, after all that preamble, I think we needed to set the scene about it, but let's come on to some of your ideas. I won't even spoil it, but I feel like you've got a bit of a rebellious spirit to all of this stuff about observers. You think that people have been tying themselves in knots a bit unnecessarily. So how do you think about all of this? How do you solve all these confusions about observers?
Yes, I think it's a huge confusion, and it seems to me that quantum mechanics should be no different to other areas of physics as far as observers are concerned. So remember, even in relativity, we talk about observers. Einstein talked about one person observing a moving train and discussed how these two different observers perceive space and time. And of course, relativity is all about how space and time changes depending on your motion. However, ultimately, you realize very quickly in relativity that observers need not be complex systems, and that ultimately any physical object can be thought of as being an observer. So you can have an atom that's moving with respect to another atom, and these two atoms will also tick at different rates if you think of them as atomic clocks. They don't need to be living systems, they don't need to be conscious, aware of anything. The physics itself will do the job for you as far as relativity is concerned. And I think personally that the same logic ought to be applied to quantum mechanics. That sometimes for educational purposes, you could use the word observer. And ultimately, of course, the physicist doing the experiment is the ultimate observer in the laboratory for all practical purposes. But there is no reason to suppose that observers are any different, just like in relativity, to any other physical system. So basically what I maintain and what I write extensively about in my book is that we can understand quantum mechanics by treating everything in the universe on an equal footing, which means atoms. We treat atoms in the quantum mechanical way, and in the same way we treat, let's say, any experimental equipment in your laboratory, any physical or biological observer that may well be there, like ourselves. All of that should be treated in exactly the same quantum mechanical way. And then you realize, if you think about it, and that's the big surprise, is that actually there are no problems anymore. All of these things that people discuss under the name the measurement problem, Wigner's friend, Schrödinger's cat, all of the famous quantum paradoxes, apparent paradoxes, actually dissolve. They are no longer there if you think consistently about it.
So that's fine, but there is something going on here, isn't there? Like we do still have a situation where we go from a superposition to a particular outcome.
Yes.
You explain this very nicely in the book, and I think what you think is going on there is, again, we can explain that with an existing paradigm from quantum mechanics, which is entanglement.
That's it.
So entanglement's an idea that confuses people. Explain what entanglement is, and then explain for us what's actually going on so that we don't need observers anymore.
Yes, I think this goes back to Schrödinger himself, really, who I think offered it initially as a paradox. I think the way that original paper in 1935 was written, he said, look, if you think that microscopic systems behave in this weird way, that they can be in many places at the same time, I can easily give you a thought experiment where that kind of weird behavior will now spread and somehow affect everything else around it. And that's the key aspect of this experiment. So basically he said, imagine that there is this atom which has either emitted some energy or not, a particle of light or any other particle. There is an emission. But because it's a quantum event, it's done both of these at the same time. It's emitted something and not emitted it simultaneously in a superposition. Then he said, if it emits a particle, imagine that there is a bottle containing poison, which gets broken by this particle, the poison gets released, and there is a cat, this is the famous Schrödinger's cat, which therefore dies as a result of that. But then he says, but if you follow the logic of quantum mechanics through, then there will be the other branch, which is equally real, where the atom hasn't emitted, the bottle is still intact, the poison is inside, and the cat is alive. And so somehow he said, if you accept a unity of physics, namely that all physical systems couple to all other physical systems, so the atom can couple to the poison, can couple to the cat, anything else that's there, then suddenly it seems that you have to acknowledge that even things like cats could exist in two different states at the same time. And I think at that time he thought that this sounded paradoxical. However, with time, and that's interesting, he evolved, I think, over the next 20 years. He gave lectures, I think, shortly before he died, in the early 50s in Dublin. And I think these lectures, if you read them, they were discovered much later, actually suggest very strongly that he thought that this is what would happen if you were to conduct this experiment. Of course, we're very far still. These are still thought experiments.
Yes.
But what I tried to do in my book is to outline experiments that may be closer to reality, which would still be in the same spirit of what Schrödinger suggested.
Yeah. So, but how does entanglement come into it, Vlatko? Because I think what you are saying in your book is that we should embrace the fact that both realities are true.
Right.
But you're replacing observation with entanglement, I think, aren't you? So tell me how that works.
Yes, and that's the exciting. Maybe again, it's easier to talk about a system like a human being could be artificial intelligence in the first instance, because maybe easier to conduct this experiment. But you want, instead of a cat, because I guess it's difficult to communicate with cats in a faithful way. We
Sure.
can't get answers easily from them.
Very difficult.
Very difficult, I think. So basically, if you imagine that there is another person inside, who simply has to register whether the atom, forget even about the poison, you don't need to make it as dramatic as that. You simply want to know whether the person has observed this atom emitting light or not. Is it a definitive outcome? What this experiment would suggest is that in each of these two branches, this person, whoever is inside the lab, feels that the outcome is definitive. So in one branch, the person will see that the atom has decayed and will simply behave in that way, that they detected that. And in the other branch, the person will simply realize that there is still no detection, and they may, record that observation, communicate it to someone else. And these two branches can actually still, and do according to quantum mechanics, exist simultaneously. However, in each of these branches, each of these observers, if you want to call them as such, feels that they've seen a definitive outcome. So it's very interesting what Schrödinger is telling us there is that there is a relativity involved in quantum mechanics as well, and it's relativity as to what's been observed and what's not been observed.
Yeah.
So there is a person in one branch seeing one definitive outcome, in another branch seeing another definitive outcome. And now we are going down the road of Wigner, where he says, but what about the person outside of the lab who hasn't really communicated with the person inside? According to Schrödinger, this person would be forced to write the full superposition down. They really would not know which of the two branches are actual. And that's what's amazing, that you have three different perspectives. They peacefully coexist. It's all nice and consistent within quantum mechanics. And until the outside person goes inside the lab and asks their friend, which is why it's called Wigner's friend, the outside person simply has to acknowledge that this is an entangled state.
So with Wigner's friend, you have a person inside a lab and they make a quantum measurement. So
Yes.
they work out, has the particle emitted something or not.
That's it.
And they've determined it.
Yes.
And then you have another person outside the lab.
Yes.
It's a sealed lab.
Yes.
They still don't know. So from their point of view, the particle is still in a superposition.
Yes.
So the question that the Wigner's friend paradox raises is which observer is right?
Exactly right.
That's the question,
exactly right. So it seems paradoxical, because you would think that once you've observed something, it ought to become a fact for the whole universe.
Yeah.
If you see the atom has decayed, surely everyone must agree with you that this is the case. However, quantum mechanics suggests exactly opposite to that. And that's the interesting conclusion here.
So that's interesting. But
Yes.
what I want to understand is, how does entanglement come into it?
Entanglement simply captures this state that in one branch, you have the person inside the lab see one outcome, and in the other branch, if you like, the word here is they are correlated to a different state of the atom.
Yeah.
And it's exactly this quantum state that describes this kind of correlation, which we call, or Schrödinger introduced this terminology, an entangled state. Yeah. So basically what this tells you, I can describe it a bit more concretely. If you come into the lab, you yourself can either talk to the person to find out what's going on, and because that person is correlated perfectly with the atom, when they tell you, you know that reflects exactly what happened to the atom. Or, and that's the interesting now thing, that you can actually exchange the observer and the observed, and that's a point I make in my book. You can go and see what happened to the atom. And let's say you see the atom has decayed. You know that if you now talk to your friend, the friend must confirm that the atom has decayed. And that's what it means to be entangled. you have two systems, an atom and the inside, the experimental physicist, who are basically in this quantum state where if you understand what happened to one of them, you automatically know what happened to the other one as well.
Yes. So I'm going to summarize it and you tell me if I've got it right, Vlatko. So I think what you're saying is that, we traditionally think of like an observer, and that language conjures up questions about consciousness. It's troublesome. We think about an observer looking at a quantum system, an atom, making a measurement. What we should really think about is not any of that language about consciousness, but it's when we make a measurement, what we're doing is we're becoming entangled with that system. And if you use that lens, any time that two things become entanglement, that's what really matters.
Exactly right.
Okay.
So in fact, that's where you remove the need for observers. You could now say, why do I need an experimental physicist? Can't I just get another atom to entangle to the first atom? And wouldn't that constitute an equally good observation? And my answer is yes. That's right.
Yeah. So I want to take it one step further. What happens then to the other part of the superposition? Does this interpretation mean that there must be a multiverse of other, because you started to use the words of branches.
Yes, I think you're right. You're right that it goes in the, I think the closest interpretation is certainly many worlds interpretation. The trouble I have with that is that it describes a very extreme possible state of affairs as far as quantum mechanics is concerned. So I think it doesn't quite even though it sounds weird already, it sounds science fiction and mad. In fact, it's not mad enough as far as I'm concerned. And so I think what would be better to say is that there is perhaps only one universe, really. And I think many people do object to many worlds by saying, well, am I now accepting, exponentially many worlds that are created?
You can never test that or whatever.
You can never test that. In fact, probably it's more correct to say there is one universe, but all the objects inside that universe are really quantum mechanical. So you acknowledge that they have this full spectrum of possibilities of existing in many different states at the same time as far as any property that they have is concerned. So they can have many different locations, many different speeds, many different energies at the same time. Anything you can think of exists in this multiplicity.
Let's move on a little bit. We've established that you think that observers is a bit misleading.
Yes.
It's a useful pedagogical tool.
Indeed.
Maybe.
Yes.
But it's unhelpful.
Yes.
Ultimately.
Yes.
And I think, if I've understood what you're saying in the book, like I feel like a big theme of the book is let's take quantum mechanics almost at face value.
Yes.
Like it already contains what we need to understand reality.
Yes.
And so we've talked about how that applies to observers. Let's turn to the small matter of particles now, because I think you also have some views about if we really take quantum mechanics at face value, it tells us some interesting things about how we should think about particles. Tell me about that.
Yes, this is also a fascinating story, and I think maybe a good way to talk about it is to simply argue against this view that when you make an observation, people say sometimes you've collapsed the superposition. Let's say you collapse one property, it's vanished, and now it has a different property. I think that's, again, unhelpful to think in that way, because I think you didn't really collapse anything in a way. When you measured the location of a quantum particle, you didn't destroy the quantum property that exists there as a position. It's still there. Dirac called them Q numbers. So these quantum numbers that underpin everything according to this view, they're still there. You can't destroy them any more than you can destroy a position of a classical object. You have a car standing there or it's moving with certain velocity, you can change the position of the car. You can change the speed at which it moves, but you're not destroying the properties that this object has. And I think we should be thinking about quantum objects in the same way. It's just that the quantum properties have this weird feature that they can exist at the same time. That's why they're Q numbers rather than see classical numbers.
And just for people who don't know the difference, a classical number just means 5, 11.
That's it.
A quantum number is a table with lots of different ordinary numbers in it. Is that the
that's
picture?
it. Lots of numbers. And actually Heisenberg, that was the first paper really that people agree was the beginning of quantum mechanics. He literally took these classical properties and made them into these tables of classical numbers, into matrices, basically.
Yeah.
And the key thing of these Q numbers, of quantum numbers, is that the order in which you multiply them matters. And that's what's behind Heisenberg's uncertainty. So if you take a position as a Q number and multiply by speed as a Q number, you're not going to necessarily get the same number if you invert this.
Yes.
Whereas classically, of course, 3 times 5 is the same as 5 times 3.
Yeah.
So I think everything should be thought of as being made up of Q numbers. And again, when you observe something, you are not destroying the Q number, but what you are doing is your Q numbers, if you like, are correlating, are entangling themselves to the relevant Q numbers that you measure. So maybe a good picture here, a good analogy would be, imagine you have a die, and there are 6 numbers that you can get. You roll the die. And of course, now you see only one number come up on the surface. But you wouldn't say the other 5 numbers are destroyed. You're just not looking at them. So now I'm thinking of a die as being a representative of a Q number.
Yeah.
And you could say, but if someone is looking from one side, they're going to see a different number. Absolutely.
Okay.
That's exactly this multitude of different perspectives,
That's
like Wigner's friend, that you get in quantum mechanics. And you don't destroy the die. When you see only one number, you know that the other numbers exist. But of course, you need to perform different experiments to possibly then reveal them.
Yeah. So I'm wondering where this takes us then. You're saying that we think about particles, it's a little bit like when we talked about observers. Particles are this thing that we have in our mind. We might think of them as little tiny balls or something, even though we know that's not quite right.
Yes.
But what you're saying is, no, we should actually be thinking about, we should take quantum mechanics seriously. Quantum mechanics talks about these Q numbers.
That's it.
And that is what's real, not the particle per se.
Yes, and that's, I think to me, that's a mind-blowing conclusion, that actually not just particles of light, which are massless like photons, but even bits of matter could actually be created, destroyed. They could exist in this superposition of being created and not created simultaneously. And in that sense, what this reveals really is that there is a deeper underlying reality which cannot be created and destroyed. And these are the Q numbers, but what you are creating ultimately and destroying are particles. And in fact, this is yet another aspect of quantum mechanics that sits very well with relativity, because in relativity we know that we can convert particles into other particles, into energy even. We can convert energy back into particles. So all of these conversions can be accounted for in quantum mechanics precisely because of this Q number-based reality.
So at the beginning of this conversation, you were talking about trying to kind of find problems to work on that would be interesting and tractable.
Yes.
I think from your book, at this point where we started to talk about particles and Q numbers, you had some ideas for some new experiments that we could do that might actually reveal, as per the title of your book, a new reality. So can you tell me a bit about the experiments that you have in mind in this area?
Yes, I think that there are many interesting experiments that could be done. One certainly could be the experiment that really shows that particles are not fundamental elements of reality. And to describe it in a very superficial way, but I think it gives you the key, the gist of the idea there, is to make, let's take an atom. If you want to do that with an atom. Of course, you could take a smaller, simpler system, but I think with an atom it would be amazing, because we're all taught that atoms are we start by atoms, they're the fundamental elements, everything is made up of atoms and so on. So if you are able to put an atom in a superposition of being in 2 different places at the same time, what you now want to really test is that what the ultimate elements of reality are the Q numbers that pertain to each of these locations, and not necessarily the existence or non-existence of an atom in these places. And I think that's why first you need a superposition of an atom, and then you need to execute certain measurements in each of these places. In fact, what you're really testing is the amount of entanglement between these two locations in Schrödinger. Schrödinger would automatically recognize this as an entangled state, because if the particle is not here, then it's sitting over there, and vice versa. So there are two branches of existence. And so these are experiments that would be very similar to what's required to violate Bell's inequalities. Like any standard test of entanglement is basically what you would have to do here. Yeah. And what you would rule out is, if you were to violate Bell's inequalities in this case, if you would really show the quantum property of this,
which would mean that Bell's inequality being a test that shows something is entangled.
That's right. Yeah. It goes beyond the classical logic. So that would rule out the interpretation where you could say, well, wait a second, is it possible that the atom really is here or not here? It's just that I don't personally know, which is what frequently some people maintain, that it's our lack of knowledge.
Yes.
Otherwise, it's all fine. Things really exist or they don't exist, but it's just that I'm not aware of that. Until I walk into that room, I don't really know.
Yes.
This one rules this out completely, because it says, no, it's nothing to do with that. If you were to suppose this kind of underlying reality, you could actually not violate Bell's inequalities. These would be hidden variables in the jargon of physics. So you can do a very simple experiment to show that any quantum, it could be light, and actually experiments have been done already with photons of this kind, and
they showed that you were right.
And they indeed showed the violation of Bell's inequalities. With atoms, it's much more challenging. They are really just technologically harder to do, but it seems to me that's one of the experiments that we could be doing.
Yeah. So you're saying that if you've got an atom which is in a superposition, it's in, let's be sort of a little bit hand wavy and say it's in two places at once.
That's it.
So normally physicists wouldn't think, so entanglement would be between two different particles.
Yes.
But what you're talking about is an experiment that would show that this particle that's in two places at once, as it were, is almost entangled with itself, which seems to suggest that it's these Q numbers that represent these two places that are therefore the real thing.
That's it.
Am I getting that roughly right?
You're getting it completely right.
And how far do you think we are away from that? Is that like we could do this next week? Is this years away?
I don't think it's years away. I think people who are doing these Bose-condensates and cold atoms do have the right technology to do that.
And a Bose-condensate is a
Bose-condensate is like a collection of sometimes up to 1 billion atoms, which are all cooled down to a ground state, the lowest energy level, and they basically exist in a huge superposition, in a huge quantum mechanical state. And I think with systems of this kind, we could do this experiment.
So we've established that observers don't exist, or at least that's your view.
Yes.
We've established that particles don't exist. We're going to come on to sort of space and time in a moment, but I just want to pause just for a moment before we move on and get you to kind of reflect a little bit, because you started to talk a little bit there about sort of other interpretations of quantum theory. Some people embrace the kind of observer thing a lot more. They go the opposite direction from you, and they say quantum theory just tells us about our knowledge. It's not a description of reality that out there. It just tells us what we know about reality, a subtle distinction. I guess I want to kind of get you to reflect, like how radical are these ideas that you're, would people generally accept them? What do you think?
I think they are considered less and less radical now. Certainly 20, 30 years ago, I think they would be considered very radical. And you're right that the Copenhagen view, which is still is the predominant view, I think, of quantum mechanics, would probably advocate a very special place for an observer. And not only that, they would insist that this observer must be a classical system. And I think that's the distinction that I'm
meaning
arguing
something
against.
on the size of a macro world.
A macro world,
object.
and that means that when they see an outcome, it's definitely like that. It's everywhere like that.
Yes.
And in fact, I'm arguing precisely the opposite way, that all the apparent paradoxes that we think might be related to quantum mechanics come from the fact that we are introducing this double standard, if you like.
Yeah.
We are saying, look, this small part of the universe is really quantum, but when we engage from the outside, suddenly everything becomes classical.
Yeah.
And actually, even mathematically speaking, it's very difficult to put classical and quantum equations together in a consistent. I think all our apparent contradictions simply are a consequence of this wrong view of reality, that there is a classical world out there, ultimately.
We've ticked off observers, they don't exist. You say particles also, we need to think instead about quantum numbers. That's what you're saying.
Yes.
So we're going to talk a bit more about like the future of physics. But before we do, I want to just sort of tick off space and time as well. You know, the minor matter of space and time. I think you feel that space and time also is more of a pedagogical tool than something real.
Yes, I have an argument. Again, this goes nicely back to what we discussed in terms of the problems that you try to focus on as a theoretical physicist. You are thinking, where do I think is something that's really genuinely problematic, and it's going to give me something fruitful that goes beyond what we expect. And of course, no one ever knows. All of these experiments that we are discussing could always go the other way.
You could be wrong.
I could be wrong easily. I could easily be wrong. And actually, that's part of the excitement, is when you notice that there is a controversy. One of the indicators whether you're thinking about the right problems is a huge disagreement in the community. That always tells you that this is interesting. It's unresolved, and it should be at least experimentally understood better. So having said all of that, the question here is really how to understand quantum nature of gravity. Is gravity quantum mechanical? So we talked about these two theories that are incredibly successful, the best descriptions of nature so far that humans have ever had. And the question is, what happens in domains where they need to be applied at the same time? Does that mean we have to classicalize quantum mechanics? So that would go along the lines of maybe what people who support observers and classical observers would argue. Well, maybe gravity is your ultimate classical observer. Maybe things stop being in quantum states at that time. The other side, which I think I'm more inclined to support, is that actually, no, it means we have to quantize gravity. All of the relevant degrees of freedom, and that's, I think, where space and time now enter, everything that we think captures classically gravity needs to somehow now be converted into these Q numbers. Everything that's a classical number, and in Einstein's relativity, everything is a classical number. You have to now try to think of that as quantum numbers. And the question is, what does that mean? What should I now upgrade from classical to quantum numbers? So you've got approaches to quantum gravity which argue that space and time should be quantized. And there are many approaches of this kind.
That would be things like, I know that as you said there are many, but just to sort of put in context what that means. So for example, you might say that space-time itself comes in almost like little atoms.
Indeed.
For example.
That's exactly what it means.
Okay.
That's right. So people would argue that there is the smallest fundamental length that we can measure. There's the smallest fundamental duration of time that we can measure. No one really knows. We can speculate what they might be. So, you know, these Planck's times and Planck's distances come to mind, but we don't really know. We don't understand that domain very well. So that's one possibility. But another possibility, and that's the one that I'm arguing for, is that what we really need to quantize is the field that leads to gravity. So that you should actually be thinking of gravity not necessarily the way that Einstein originally thought about it and the way that we described it as bending of space and time, which is, I think, how we're traditionally taught this as well. But we should think of that more like the way we think about the electromagnetic field, that there are various components of the electromagnetic, you know, there are the three electric, three magnetic components and they exist in all places in space and they change in time. But the space-time is more like a convenience grid for us to describe things in a very shorthand manner, if you like. So I can always tell you about the location by pointing to something else. You know, if you ask me, where did you measure that electric field? I could say, oh, it's where that chair is or where that table is. So I never need to give you the full coordinates for that. I can always talk about it relative to something else.
Yeah.
And it seems to me that gravity, that it's much more fruitful to think about quantizing gravity as quantizing these fields, converting these C numbers from Einstein's theory into Q numbers to obey quantum mechanics. And of course, the key question there is, can you test that?
Yes.
And I think that's...
Before we do, again, I want to make sure I've understood correctly.
Yes.
So you're kind of saying that in the classical picture of general relativity, we have this field called space-time and it can bend.
Yes.
You're saying, actually, we don't need that because we already, in quantum mechanics, have this field which we call the electromagnetic field, which mediates things like magnetism, but all sorts of other things as well, most of the forces that we experience in life.
Yes.
And that field is already described in the language of quantum mechanics. And you're saying we can just use that field instead of space-time?
No, I'm not saying
Not
we can use it necessarily instead. I'm saying we should treat gravity in the same way that we are treating electromagnetism. So the way that we quantize electromagnetism, we don't quantize the space-time locations on which these fields sit. We simply quantize the fields.
Okay.
And space-time just remains a classical grid. There's no problem with that.
So it's the Q numbers again, isn't it?
It's always the Q numbers.
It's just Q numbers.
That's right. And that's the key thing. As I'm very happy to admit, obviously this may be contradicted by our experiments. So there is no guarantee that this will come out this way, that they will come out as Q numbers.
Yeah.
And it's already extremely exciting that there are so many views. People who agree with this point of view, people who disagree with this point of view, which really tells us that this is something that's exciting to test.
Yeah, I want to talk about the future a bit, but before we do, I just wanted to ask about experiments, because you were just saying, I could be proved wrong. Is there an experiment that could help us probe what you're saying, the ideas that you've just put forward about how we quantize space-time?
Yes, so what I wanted to do in the first instance, and that's the most accessible experiment, is to really show that there are at least some quantum numbers that you need to use for the gravitational field. So even before we understand in detail what exactly needs to be upgraded into Q numbers, I wanted the simplest experiment that would at least force us to acknowledge that some Q numbers must be introduced. Otherwise, we can't model this. It's a bit like Bell's inequalities, that when you violate the Bell's inequality, you know that the state is quantum. You may not necessarily know all the details of your state. You haven't probed all quantum aspects, but you know some aspects are definitely.
You've kind of crossed a threshold.
You crossed the threshold, and I want that kind of threshold experiment. So Chiara Marletto and myself and Sugato Bose, independently, we came up with a very simple idea, which is kind of a variant of Schrödinger. I think all experiments ultimately in quantum mechanics are variants of Schrödinger's cat. But you're not doing, of course, you're not involved. No cats involved again. Yeah, that's right. That's right. That's it. So basically, what you want to do is you want to take two sufficiently large objects. Now, I'm saying this from the perspective of atomic physics. They're still tiny.
Sure.
But they are large in the sense that we've never put anything as big as that into a superposition of two different locations. And now you need two objects like that. You need to take one mass, put it in a superposition of two different places, and another mass, and in a superposition of two different places. And now the question is, how does gravity couple these two masses?
Okay, yeah.
Now, is it going to go in the way that I'm advocating, that you're going to have a gravitational force between each of these locations of one particle and each location of the other?
Each of the superpositions.
Exactly.
Yeah.
This is your branching, exactly as Schrödinger envisaged. And this would lead to entanglement between the two masses, and that would be your witness now. If you could violate Bell's inequalities or do any equivalent experiment, you would actually show then that whatever mediates this kind of entanglement must be quantum mechanical. You could show that you cannot do it otherwise. So this experiment is basic in the sense that if you ask me then, but which degrees of freedom are quantum mechanical?
And what do you mean by degrees of freedom?
That's right. So which aspects of the gravitational field are quantum mechanical? Going back to our discussion, is it space or time?
Yes.
Is it the components of the gravitational field? This one wouldn't be sophisticated enough to necessarily answer. Both would be possible.
Okay.
So this would only tell you that gravity certainly has to have some quantum components, and that kind of closes at least that part of it can't be all classical. You can no longer kind of have this dichotomy in the universe. At least some parts of gravity must join this. If you want to know more, I think we would have to get more sophisticated, really, to go in the direction of probing exactly what accounts for
Which
this
is much more difficult.
And
presumably.
that's much more difficult.
Yeah. Let's start to come into land and talk about the kind of we talked about experiments that we are quite probably many years away. Let's go even further.
Yes.
And in your book, you start to talk about this idea of kind of taking the equations of quantum theory, and you say that there's kind of some unfinished business. I think there's some bits of these equations that aren't really quantum.
Yes.
And you're saying, well, if we make those quantum, we could sort of have some quite interesting and quite pretty bold predictions.
Yes.
So let's start to explore that a little bit.
Yes, this is, I think, an extremely important question. And actually, the message that I try to emphasize is that that's where the interpretations of your theory are extremely important, because they are your guide as to what kind of questions you want to ask. So if if you believe that there is part of the universe that's intrinsically classical, you will never be thinking about experiments that try to engage that bit of the universe in a quantum mechanical way. So even though you could argue, well, at present we can't tell which of these interpretations are kind of correct and which are not maybe a good reflection of reality. That's true at present. However, which interpretation you subscribe to determines exactly what kind of questions you'll be asking. And I think that's where this is important. That's why I'm advocating taking quantum mechanics seriously and going even further down that road.
Yeah. So as an example, again, tell me if I'm getting this right, but like something like the speed of light.
Yes. Yes.
That appears in the equations of quantum mechanics.
Yes.
But it's not a quantum number, it's just a number.
That's right.
299.
Yes, that's right.
However, I can't remember the exact figure.
10 to the 8, that's it, meters per second. Yeah, that's it.
But it's just a number, a very big number.
That's it.
So most people wouldn't think like, well, we should quantize that. Most people just think, well, that's just the speed of light.
That's right.
But you're starting to think, well, actually, hold on, what if the speed of light were quantized?
Exactly. I think it's a very important point, because the way we do, it's exactly what we discussed. The way that we come up with quantum mechanical descriptions is we take the equivalent classical description and then we upgrade some of these classical numbers into Q numbers. But then the question immediately comes up, if you really think of everything being quantum mechanical, is what about these other things that we haven't quantized? Why is that the case? Maybe there is a fundamental reason why they ought to stay classical, but if this is the case, then we ought to test it, whether they're also quantum mechanical. So in the full generality, whenever we couple two different fields in quantum mechanics, if you take the field, let's say, of electrons, and you couple it to the electromagnetic field, which accounts for electrodynamics, most of electrodynamics, there is always a bunch of constants that sits in front, which involves things like the speed of light, as you mentioned, where basically it tells you how strongly these two fields couple to one another. And the question is this really just one number? Has the universe really just determined that this ought to be one number? Or what would happen if we also quantize things like that? And I think this is an interesting question to go fully with this program and really try to come up with the full quantum mechanical description, leaving no places anymore for classical numbers, if you like.
Yeah.
And the interesting thing is that, yes, this has consequences. What this would suggest is that there are systems which we didn't think of previously as quantum mechanical, which now have to be assigned to this new thing that you upgraded from a C number to a Q number. So it would suggest things like possibly the electrons don't couple directly to the electromagnetic field, but there is an intermediate quantum system which would now arise from this extra quantization, which would actually mediate this kind of coupling.
So the logic here is that, going back to one of the threads that's run through this this conversation, is the idea that Q numbers are, you think, kind of the essence of reality.
Yes.
So what we're saying now is, if we take some constant that appears in the equations of quantum mechanics, and we make it into something that's composed of Q numbers, by definition, those numbers, and we're saying those are the really real thing, they should be able to be entangled with other aspects of reality.
Exactly right.
Okay, so that's where we are, and that's kind of what you're suggesting we probe.
That's right.
Let's come back to our experiment. Does this suggest, could we ever probe that with experimentation?
Yes, I think so, because that's again always goes back to entanglement, which is very interesting. So what you would be probing is the degree of entanglement between the two things that you knew were quantum before, and then the degree of entanglement that you would calculate if this extra quantum system was really there in place. So, and there is in quantum information, there is something that we call monogamy of entanglement. And monogamy of entanglement means the following thing. If two things are really maximally entangled, that means that neither can be entangled to anything else.
Okay.
And that's what you are testing.
Yeah.
So in the former theory, it would say the electron gets fully entangled with the electromagnetic. There's nothing else in this connection. If there is an extra quantum system, you would see reduced entanglement between the original two systems because of the presence of the third system. So these are the kind of things we should be looking for.
So you would infer it from that.
Infer it indirectly.
You would see less entanglement than you expect.
That's right.
Yeah.
So it doesn't necessarily mean that you would have to directly detect the quanta of this. It could be that there are quanta of this extra system, and maybe you can detect them. But even if you couldn't, you could indirectly infer the existence of this extra system.
And what would that look like if the speed of light was quantized? What does that, my head slightly explodes, like what does that mean? Does that mean there's some extra field? I don't quite understand.
Yes, that's right. There would be extra field then that would be associated with this. Like I said, there could be quanta of this. It would also force us then to understand why, for all our practical purposes so far, we can get away with only a single number. Because the first question you should be asking is, could I then come up with situations where I would get these other speeds to be relevant and so on?
I just want to touch on, I don't know if I dare open this can of worms, but what about time? Could one apply that logic, like we were talking about, quantizing something like the speed of light? Could you consider time in that way, and what implications would that have?
I think that's one of the chapters in the book even explores that separately, even without going into the full general relativity. You can do experiments with time separately, and I think that's also mind-blowing. So you could actually test this idea that time flows at different rates for different observers. If the observers are moving at different speeds, as Einstein said, they would perceive time differently. You can actually now take a single particle, a single atom, you make it into a superposition of two different places. And in one of these places, you take it on a journey and back. This would be like the twin paradox that Einstein called it. But of course, he did it with two twins. Here you are really doing it with a single quantum system, but it's just in one branch of this superposition, you take the atom on this journey and bring it back. And when you bring it back, you've got still one and the same atom, but it shows two different times because of quantum mechanics. And that sounds, no one has done this experiment.
No. Yeah.
And I think it's doable, and it seems to me an immediate consequence of quantum mechanics as well.
What would it mean for the particle?
That's right.
I can't even wrap my head around it. It would mean that the particle somehow has two times.
Yes, and this beautifully, indeed, and this goes back to this thing that different observers, if you want to call them again, can ascribe different properties to one and the same system. So in one branch you've got one time, it's superposed with there's a younger version of the particle and older version simultaneously sitting in the same location. And the person doing the experiment has their own clock. There is yet another time in the laboratory, which is equally good for that purpose as well, but it's different to the other two times as well. So there are these multiple perspectives that all exist simultaneously within quantum mechanics. And I don't see any reason why the same shouldn't be true for time.
So we've covered a lot of ground. We started with observers, we've talked about particles, space and time. We've even talked about two particles having two different times, which I'm still not completely sure I understand. But I guess just to wrap up, we've also talked about a lot of experiments that you have proposed.
Yes.
What I wanted to get you to do as we close Vlatko is imagine that perhaps it's 10 years in the future, your book has sold really well. Physicists have embraced these experiments and we've done all of them. And let's imagine that they've all worked out exactly as you think they will. It's all gone your way.
Yes.
How does that change our picture of reality? Because your book is called Portals to a New Reality. Paint me a picture of what that new reality would look like if it all goes as you think it will.
Yes, I think that's the key question. Again, that's what all of us in physics would really like to understand ultimately. So I think if these experiments came out the way that I'm predicting, that would really tell us that we should be thinking about unifying our two key theories, general relativity and quantum mechanics, in a very specific way, which is the one that I'm advocating, which is to upgrade these classical properties in general relativity to these quantum numbers. Again, the experiments that I suggest only take us a certain way. As I said, there will still be a lot of open questions there. How far should we go down that road? So the other extreme, for instance, which I don't really discuss much, are the very, very strongly gravitating systems like black holes, for instance. So that's the one where gravity is so strong that it certainly could be that there are new effects coming out of there when you merge it with quantum mechanics. So the experiments I have in mind are really lab-based, and they involve relatively weak gravitational, so that would be like the first order corrections to Einstein's theory. So certainly if they were confirmed, I think it would tell us that we need to probe more of these properties and see how far this goes. Is it really true that the whole of general relativity needs to really be quantized ultimately, which is one possibility. And that theory may be a completely different theory in the sense that it may give us quantum mechanics and general relativity as two special limiting cases of this theory. But in fact, it could be a much larger theory predicting completely new phenomena.
Yeah. So it would in a sense put us on a new path.
That's it.
But we don't quite know where that path's going to end up.
Yes, I think it's very similar with any revolution that we had in physics, a bit like with quantum mechanics, that with Max Planck, we knew that we needed to discretize energy in order to explain black body, but he couldn't quite anticipate how far this would go, that it would spread to atomic structure and everything else, really, ultimately.
Vlatko-Vatral's theory, if true, would be transformational. But it concerns things at its core at the very smallest scales. At the very largest scales, at their most extreme, like at the center of black holes, reality also starts to break down. Physicists have puzzled over this for decades in what's known as the black hole information paradox. In this next video, we're going to see how physicists have struggled to understand what happens outside the boundary of black holes.
Behold, Sagittarius A star, 15 million miles wide with a mass of 4 million suns. It's located smack dab at the center of our galaxy, but don't let this picture fool you. The black hole itself is invisible. You'd be drifting towards this object that's millions of miles wide, and you could never see it. You could only ever see the light swirling around its edge and the space twisting and tearing as it pulls everything in. Sagittarius A star is what's known as a supermassive black hole. And supermassives are sort of a fan favorite, but they're really just one of many different types of black hole that exist. Now, we've been covering black holes for decades at New Scientist. We publish so much about black holes. So today we pulled together everything our experts know about these mysterious and terrifying astrophysical objects. Part of the reason why we love black holes and why physicists are so fascinated with them is because they're kind of where all our best theories of physics break. Grasping them, really understanding them, will require us to paper over the cracks of physics that exist today. It will require us to reconcile quantum mechanics and gravity, and it will require us to understand space-time like we've never understood it before. There's also something really mysterious about black holes. How do you detect something you can't really see? Maybe we can hear these invisible objects collide over a billion light years away. And how could an object known for trapping everything slowly evaporate into nothing? So I hope you join us as we go a bit deeper, because the closer you look, the more unsettling things become. Some black holes were already supermassive when the universe was still in its infancy. Others might be baby black holes left over from the Big Bang, now hiding anywhere, maybe even in our own solar system, and possibly holding the key to dark matter. And once you get to the center of it all, you'll hit two problems that still haunt modern physics: the singularity and the question of what happens to information when it falls into that singularity. Those are the mysteries that we're going to unpack in this video. We'll cover different kinds of black hole, from the ones we've already observed, supermassives, missing links, and more, all the way through to a wacky assortment of things we think could solve our problems with black holes, like wormholes, gravastars, and these things called fuzzballs. So let's get started. First things first, the basics. Black holes are simple. I'm serious. Now, each of them can be described with only 3 numbers: the mass, the rotation, and electric charge. And yet they challenge our understanding of the rules of which our cosmos is arranged. There are 3 kinds of black holes for which we have strong observable evidence. The most common variety, your garden variety of black hole, is known as the stellar mass black hole. Stellar mass black holes are everywhere. There's millions scattered across the galaxy alone. They form when a star no longer possesses enough fuel to generate this outward pressure and instead succumbs to gravity, first in a dramatic supernova explosion, then collapsing in on itself. Okay, so hold that thought. This is a good time to ask a few basic questions. For starters, what is a black hole? Well, you might have seen a diagram like this before, or have heard Einstein describe space-time like a fabric that stretches and distorts when mass is placed in it. That warping describes how objects with mass all have a gravitational field. Things that travel close to an object fall towards it, rolling across the natural curve of this fabric. Now, only a few months after Einstein published his equations describing this effect, a guy called Carroll found a pretty alarming result. He said that if you had a mass that was big enough, compacted in a small enough volume, it would cause space-time to diverge and just curve into infinity. We call that a singularity. Now, the curvature and gravitational pull of these regions be so strong that light that gets too close to the surface, known as the event horizon, it would just get trapped. And as a result, black holes would appear to us as pits of darkness, like that's why they're called black holes. But they would have these bright, wobbly rings of light around them as light skates across its surface. Now, Einstein was skeptical. To him, this seemed like a mistake, like maybe it existed in the mass of general relativity, but we never really see them. But we have actually observed them. Now, if you imagine an invisible household vacuum cleaner, Even though you could not see the appliance itself, you'd know it was there because bits of dust would react as the vacuum cleaner approached. In this way, beginning in the 1960s, telescopes began spotting black holes by how stars and gases behaved in the immediate vicinity, seemingly orbiting empty space. Since then, our sleuthing abilities and tools have improved. In the mid-1990s, astronomers began tracking the orbits of several stars circling a source of radio waves. And it turned out it was emitted by our good friend, Sagittarius A star. The next big leap in black hole detection came in 2016 when the Laser Interferometer Gravitational Wave Observatory, try saying that 3 times fast, aka LIGO, witnessed a collision between 2 black holes. This clash created ripples in space-time. It's precisely the ones predicted by Einstein's theory of general relativity. Fast forward 3 years, and scientists have published a holy grail of sorts, the first ever image of a black hole. In this case, a supermassive. Now, as the name implies, supermassives are like the much larger sibling of stellar masses, and they're not only a little bit larger, they're much, much larger. This brings us on to the monsters living in the middle of our galaxy. Now, a typical stellar mass black hole stretches 30 kilometers wide across its event horizon. That's 15 miles for Americans. As for the Milky Way's resident supermassive Sagittarius A star, try multiplying those numbers by roughly 1 million. The matter contained in black holes is measured in what is known as a solar mass. That's the amount of mass contained in our planet's sun. Now, as the name implies, supermassives aren't just insanely huge. While the mass of a stellar mass black hole ranges from a few suns worth to up to a few dozen, the largest known example of a supermassive black hole contains the mass of our sun 66 billion times over. But it's highly compacted. In relative terms, imagine the entire Earth squeezed down to the size of an object 2.5 centimeters across. That's 1 inch. Like stellar mass black holes, we surmise the existence of supermassives long before we ever even saw one. Over half a century ago, scientists identified these things called quasars. They're the brightest known object in the universe. They speculated that the quasar's blinding light was caused by an amount of heat that could only be generated as matter approached the event horizons of these colossal black holes. As matter enters these supermassives, something known as an accretion disk is formed. This concentrated plasma is propelled by the black hole's rotation. Now, the first ever snapshots removed most of our lingering doubt regarding the existence of black holes. And even more spectacularly, earlier this year, the James Webb Telescope even managed to capture the supermassive within our own galaxy, Sagittarius A star. Now, despite their huge size, these giants are surprisingly common, sitting at the center of nearly every Milky Way-sized galaxy. Astrophysicists speculate that the ubiquity of supermassives could be meaningful, and here's why. We have observed a supermassive black hole formed over 13.3 billion years ago, a mere 500 million years after the Big Bang. That presents an appropriately enormous mystery. Based on what we know about how black holes form, how could one get that big that quickly? Perhaps rather than forming from collapsed stars, these early black holes contained the mass of many accumulated smaller objects, clouds of gas. In that case, perhaps there's a connection between supermassives and the formation of galaxies themselves. In the search for answers to that and other questions, scientists have turned their celestial gaze to the next black hole on our tour, the so-called missing link. Intermediate black holes most certainly exist. The problem, we haven't been able to find many of them. Many speculate that the formation of these intermediate-sized black holes is tied to dense collections of stars known as globular clusters. The hypothesis goes something like this. A single star expires and forms a stellar mass black hole. This then nudges nearby neighbors to collapse and join the party, and a nascent intermediate black hole is formed. Intermediate black holes contain a solar mass of approximately 1 to 300 suns. Very big compared to the stellar mass black holes, but a drop in the bucket compared to supermassives. And perhaps drops in the bucket are exactly what they are. Functioning as a sort of galactic food chain, maybe stellar mass black holes combine to form intermediates. Thousands, if not millions of intermediates then are gobbled up to beget supermassives. Hopefully you're still with me, because this is where our plot thickens and acquires a bit of mystery. Hey, it's me in the future. If you're curious about the universe's biggest mystery, there's no better place to look than New Scientist. Our company was formed in 1956 for all of those interested in scientific discovery and its social consequences. And we love to ask the big picture questions all the time about the universe, about life, and what it means to be human. If that sounds like something you like too, then why not join us? With a New Scientist digital subscription, you'll get access to all of our award-winning science and technology journalism, some edited by me, including our daily news so you're up to date with the latest developments, and our deep dive features so you're never without a captivating tale to fuel your curiosity. For a specially discounted New Scientist digital subscription, go to newscientist.com/YouTube. So, back to that mystery. The primordials. All right, small, medium, and large black holes definitely exist. We've seen them, but we think there may also be an extra small type of black hole, one that might even be key to resolving the mystery of the elusive dark energy and dark matter. So-called primordial black holes could be hiding just about anywhere, maybe even in our own solar system. These baby black holes would have begun forming immediately after the Big Bang. In the universe's earliest days, fluctuations in space-time would have created an uneven distribution in the density of matter throughout the universe, some lumpy bits in the primitive cosmic soup. In areas of relatively high density, micro black holes whose mass would have been able to be measured in single-digit kilograms may have formed. But as if locating primordial black holes wasn't hard enough, like finding needles in an intergalactic haystack, the advanced age further complicates the challenge. Stephen Hawking predicted that black holes emit a type of radiation, what we call Hawking radiation, and as they do so, they steadily shrink. Like melting ice, the smaller they get, the faster they decrease in size. Given the rate of this evaporation, primordial black holes formed shortly after the Big Bang would have already disappeared. The search is now underway for the telltale gamma rays that would represent these ancient black holes' last breath. But quite a lot is riding on it. Many believe that primordial black holes may prove to be the secret hiding place for dark matter, the elusive and invisible glue that binds our universe. But here we come to a bump in the road. What if our concept of a black hole is flawed? As our investigation deepens, additional doors open to an astonishing array of possibilities. Black holes within black holes, secret passageways to travel throughout time and space, and more. All possible solutions to a pair of very big problems. The problem. Be they ultra small, small, medium, or large, all black holes are major pains for physicists. So what was Einstein's problem with them, and why was he so opposed to the idea that they could exist when it was first pointed out by Schwarzschild? Because black holes, as we've described them thus far, break theory and they present two supermassive problems. Each relates to the idea of a singularity, the points of infinite density believed by many to exist in the center of black holes. In theories like general relativity, infinities are a sign that something is badly broken. Einstein, when he first formulated his theory, relied on space-time being made of a geometry that just smoothly extends. That's how we make the maths of general relativity and energy conservation work. But if it suddenly just veers off into infinity, it's unclear what happens to those other laws. And because of this problem, Einstein attempted, but failed to prove that black holes were impossible. And then there is the information paradox. Originally detailed by Stephen Hawking, this paradox pits our understanding of the physical world in the largest sense against our understanding of the world in the smallest. This is where we get the clash of our two best theories of reality, general relativity and quantum mechanics. General relativity holds that information about matter compressed inside a singularity should just be lost. The problem? The laws of quantum mechanics state that information cannot be destroyed. In tackling these twin challenges, scientists have attempted to tweak the equations and put forth a radical proposal that what we're actually looking at aren't singularities, but are a type of cosmic imposter. They've conjured up blueprints for alternate concepts of black holes in which the maths adds up. This process is known as regularization, and the resulting models are therefore known as regular black holes. But as you're about to see, they are anything but. Here are a trio of cosmic curveballs with quirky names and even quirkier properties. Meet string theory's contribution to the conversation: fuzzballs. One of the main strengths of the fuzzball model is that on paper, it solves both the singularity problem and the information paradox in one fell swoop. How? Well, string theorists think that reality, every particle in the universe, is actually made up of even tinier vibrating strings and membrane-like structures called brains. They think that a black hole could be a dense tangle of these strings and brains, knitted together in a compact object. To a distant observer, a fuzzball might look like a conventional black hole, but up close, the surface of a fuzzball would be like a weird quantum thicket, a strange vibrating structure, constantly absorbing and re-emitting radiation instead of just gobbling it up. The fuzzball sidesteps the information paradox by getting rid of the idea of an event horizon and singularity. Information never really disappears, it just gets entangled and stored in this mess of quantum strings in the black hole's intricate internal structure. The catch? We all, quite fortunately, live outside of black holes. And from an outsider's perspective, there is nothing which allows us to visually distinguish black holes as understood within general relativity from black holes as reimagined by string theory. The same can be said of the two additional and just as exotic possibilities. Gravastars. Another way to tackle the information paradox. What if, instead of a point of singularity at the center, you have a shell created by a type of repulsive energy? Stay with me here. We know that the universe is expanding, but we don't quite exactly know how. Some speculate that the force driving the expansion of the universe originates from something called vacuum energy. Think of it as the energy intrinsic to the fabric of space-time, even after you strip away all matter, radiation, and particles that could be in it. Well, what if black holes have a bubble of repulsive vacuum energy at their core, and this region pushes outward, preventing them from collapsing into a singularity? The walls of the bubble would be like an ultra-thin shell of incredibly dense matter, a kind of gravitational membrane. And this is the concept behind gravitational vacuum stars, aka gravastars. An even more elaborate variation of gravastars has also been suggested. These are known as knee stars. One gravastar wholly contained within another, our universe's version of Russian nesting dolls. Or how about something even more outside the box? What if black holes, at least some of them, aren't really black holes at all? This leads us to a name you've likely heard before, but contrary to what you might guess, they're not solely stuck in the realm of science fiction. Wormholes. As seen starring in Hollywood hits like Interstellar, you probably know about the basic concept of wormholes. What you may not know is that these hypothetical tunnels boring through space-time could in some ways mimic black holes. Oh, and also, they could be very real. The idea of secret cosmic doorways bridging the universe past and present may sound fanciful, but their theoretical existence is supported by general relativity. Like fuzzballs and gravastars, wormholes offer an alternative to the problematic concept of singularity. An extremely exciting one. What if something that looks like a black hole from the outside is actually one of these intergalactic portals? In this scenario, some black holes might not be cosmic dead ends, which escape is impossible, but a doorway to something called a white hole, the theoretical yin to the black hole's yang, into which nothing can enter and from which matter spews forth. Even on a theoretical level, a functional wormhole seems fairly far-fetched. One challenge would be maintaining that fragile stability. Ordinary matter has positive pressure and energy, both of which contribute to things like being gravitationally attracted to mass. But to keep a wormhole propped open, you would need something that produces repulsive gravitational effect, matter with a negative energy density. Think of this exotic matter like placing a jack under a car. Gravity pushes the car down, the jack pushes back and keeps the car propped up. For the record, NASA maintains that black holes are not wormholes, meaning the tantalizing, if somewhat terrifying, opportunity to go skipping through time and space will probably not present itself anytime soon. Everything you have learned about black holes may sound totally absurd, and yet both our theories and observations tell us that they truly do exist. We've come to the end of our story, at least for now. The next great frontier, well, that's a proposal to extend our best black hole telescope, the Event Horizon Telescope, into space. The distance between this new explorer and our Earth-based observatories would allow us to capture the most elusive photon rings around black holes in much more detail, providing a clearer outline of space-time at the boundaries where we expect them to break down. The Black Hole Explorer, if funded next year, would launch in 2031. Black holes provide an excellent playground for testing the limits of scientific possibility. They reveal profound truths about our universe and raise even more profound questions.
It's all well and good understanding physics in our universe, how black holes work or how quantum mechanics functions, but what if there are other universes? The physicist Sean Carroll in this next video is going to take us through the idea of many worlds. What if we live in a multiverse?
Thank you very much, everyone. It's great to be back here in London in New Scientist Live. It's especially thrilling for me to get to talk on the subject of today's talk about quantum mechanics. I love quantum mechanics. I think that everyone should love quantum mechanics and know more about it. It gets me so excited that I'd like to begin a talk on quantum mechanics by doing a little hop up in the air, a little physical gesture to let people know how excited I am. The problem is, I've never been able to decide, should I hop to the left or should I hop to the right? Fortunately, I have quantum mechanics to help me out. So here, this is an app you can get on your iPhone called Universe Splitter. What will happen is I will push the button, it will send a signal to a laboratory in Geneva, Switzerland, that will send a photon down a beam, and then the photon will be split left and right. And according to the rules of quantum mechanics, there's a 50% chance that it goes left and a 50% chance it goes right. According to the many worlds interpretation of quantum mechanics, both of those options actually become real in separate worlds. So there will be a world in which I hop left and one in which I hop right. Let's see which one this will be. We're splitting the universe. We've contacted the lab. The device is ready, the photon's emitted. The universe has just split. You are in the universe in which you should hop right. Thank you. According to the many worlds formulation of quantum mechanics, there is another truly existent part of reality in which I just hop to the left, and I'm right there. And that person right there, who's no longer me, it's a different person, is gesturing over to their right, saying that there's another version of me over there, okay? This is not science fiction. This is what many of us, including myself, think is likely to be true, a correct description of nature, this many worlds version of quantum mechanics. There really is another world just like that. And what I would like to do in today's talk is explain to you the reasons why otherwise sober-minded physicists would think something so obviously crazy. All right, let's get going. So before we get to quantum mechanics, the best way to understand it is to contrast it with classical mechanics. There have really been two great revolutions in the history of physics. The classical physics revolution from Isaac Newton and the quantum mechanics revolution that happened in the 20th century. So Newtonian physics, classical mechanics, this is what you learned in high school, in the beginning of university. This is what we torture our undergraduates with inclined planes and pendulums and frictionless surfaces and billiard balls and all that stuff, right? Even though there's a lot of math, you have to do a lot of problems, it's still pretty close to our intuitive view of how the world works. There's stuff, whether it's billiard balls or swing sets or rocket ships, and that stuff moves through space as time flows by. There are rules about how this happens. This rule is the laws of physics, in particular Newton's second law, F equals ma. When you put a force on something, it accelerates proportional to the amount of force, okay? Newtonian physics is a clockwork universe in the following sense. If you tell me everything that's going on in the universe, which is to say the position and the velocity of every piece of stuff in the universe, the laws of physics can tell you exactly where it will go in the future, and indeed exactly where it was in the past. There's no obstacle to measuring exactly what the universe is doing in principle. In practice, that can be very hard. That's what we were taught as youngsters, and then came along quantum mechanics. And I'm not going to give you the full, detailed historical sketch about quantum mechanics. Unlike Newtonian physics, which burst from the mind of Isaac Newton, there were predecessors, but he really figured it out all at once. Quantum mechanics had a difficult birth. It took many people over the course of years to figure it all out. So this slide is just to let you know, to remind you, that the crazy ideas we're going to be talking about in the rest of the talk were forced on us by trying to understand the data, okay? They're not things that we sat around in our room late at night with a few pints going, man, what if there were like a lot of universes out there, okay? We are driven to the crazy ideas I'm going to be talking about today by trying to account for what we see in nature. So for example, there was Max Planck, who has really launched the quantum revolution by trying to understand the radiation of hot objects. We had a theoretical understanding of that, but it was all wrong. And Planck said, well, maybe when light is emitted from these hot objects, it comes in discrete packets. But it wasn't until Einstein, 5 years later, that he said, maybe just light always comes in discrete packets. The difference is, what Planck said was basically a radiating body is like a machine that makes you 1 cup of tea at a time. Einstein said, maybe tea only ever comes in 1 cup increments. That's a much more radical idea. Maybe what we thought was a wave is really more like a particle. Meanwhile, Niels Bohr realized that if you believe electrons orbit in atoms, they should spiral in and all atoms should collapse in a tiny fraction of a second. So he said they don't for some reason. It's very, very mysterious why Bohr said that they shouldn't collapse. But then Louis de Broglie came along and said, well, maybe it's because the particles that we think of as electrons are really waves. So you see what's going on and why it was so confusing. Einstein said maybe waves are really particles. De Broglie says maybe particles are really waves. It wasn't until the late 1920s that we basically figured it all out. There were 2 people who figured it out more or less simultaneously. It looked very different, but we later figured out it's the same theory, Heisenberg and Schrödinger. And they said, put aside the idea of a particle with a position and a velocity. Invent something new, which we call the wave function, this Greek letter psi. There's not going to be a lot of equations in the talk, but I think I should show you this one equation. This is Schrödinger's equation. This is the equation that tells you how a quantum mechanical wave function evolves with time. So according to this equation, if that's all you have, it says that there's a quantum state, a wave function. You ask how much energy it describes, and that tells you how fast it's evolving. That's all you need to know. Schrödinger's equation is the quantum version of Isaac Newton's second law. Just like if you knew the positions and velocities of all the particles in a system and you knew Newton's second law, you could tell how it would evolve. If you knew the quantum state of a system, the wave function of a system, and you have Schrödinger's equation, then you can tell exactly how that wave function will evolve. So far, it seems completely parallel to classical mechanics. What's the big deal? Why does quantum mechanics have this reputation of being so hard? Here's the answer. There's an amazing feature of quantum mechanics that was nowhere to be found in classical mechanics, which says that what you observe when you look at a system is not what you see. What you see and what is really there are 2 different things. There's a difference between what a thing is when you're looking at it and when you're not looking at it. What you can possibly see is much less than what really exists. This sounds weird. This sounds bizarre. Like it's very, very different than what we had in classical mechanics. In classical mechanics, it might be difficult to observe the position and the velocity of something, but you could do it if you really tried hard enough. Quantum mechanics says that there is an unmistakable, irreducible inability to exactly observe a quantum system. You cannot observe the wave function. What does that mean? Here's what I mean. For a classical particle somewhere in space, on a billiard table or whatever, the entire state of the particle is just where it is and how fast it's moving, its location and its velocity. From that, you can predict everything. In quantum mechanics, rather than having a position and a velocity, you have a wave function that is spread out. It is what we call a superposition of every possible position it could be in. So make it very clear what I'm saying here. I'm not saying that we don't know what the velocity is or what the position is. I'm saying there is no such thing as the actual position or velocity of the particle. There is a wave function that is spread out all over the place. It's like a cloud that says for every position the particle could possibly be seen in, you assign a number. And that number is the amplitude, the wave function of the particle. That's what reality is, according to quantum mechanics. And it's not just philosophy or math. We can see it. Niels Bohr would have told you that electrons and atoms move in circles, kind of like the solar system. Real quantum mechanics, as we now know it from Heisenberg and Schrödinger, says, no, it's not like that. There's a cloud, and this cloud is an actual photograph. This is data. This is a very, very careful physics experiment that has gone in and seen exactly where the wave function of an electron is in this particular atom. So it's a completely different view of reality. The question you should be asking is, why does reality look normal to us at all? Like if really reality is a superposition of all these different possibilities, why do we see things in locations? Why do I look at the chair and say, there it is? Why don't I see a probability cloud all over the place? We don't know. That's the short answer. This is what we debate about. This is the controversial question in quantum mechanics. We do have a story that we tell our students, our unsuspecting students who we can threaten with bad grades and so forth, so they have to listen to us. We call this story the Copenhagen formulation of quantum mechanics. And basically it says the following thing, that there is something special about measurement, that the act of observing a system plays a crucially important central role in the formulation of quantum mechanics, according to the Copenhagen interpretation. And what happens is you have a cloud of probability spread out all over the place, the wave function, but when you observe it, you see the electron or whatever in a certain position. And after you observe it, the wave function collapses right away, boom, and now it's completely concentrated where you saw it. So there's a dramatic, instantaneous change in the state of the system from being spread out all over the place to bang, being in one location when you made that observation. Okay, so what is the relationship of the cloud to the observable outcome? The relationship is that the cloud tells you the probability of getting different experimental outcomes. That wave function, which is a number, it can be, let's say, a large number in the center where the blue is very dark, a small number very far away. The rules of quantum mechanics in the Copenhagen interpretation tell us, if you want to know the probability I will see the electron in a certain location, tell me what the wave function is and I will square it. Just take the quantity squared. That's the probability. This is known as the Born rule in quantum mechanics. Okay? This is what we teach our youngsters today. This is how we teach them to use quantum mechanics. The problem is it is bizarre and crazy. This can't be right. What we teach our students cannot possibly be how nature works at a fundamental level. For one thing, it should bother you that things like measurement and observation seemingly play a central role in how you formulate the laws of physics. What were the laws of physics doing before there was anyone measuring things? And what do you mean by a measurement anyway? Does it have to be a conscious human being? What if I bump into an electron by accident? Can a rock or a virus or an earthworm do an observation? How fast does it happen? How quickly? When does it happen? How close do you have to be? What if you only look at it from the side? Does that count? None of these questions have answers in the traditional textbook Copenhagen way of teaching quantum mechanics, much less why is any of this true? Why is there an approximately classical world? Why is there probabilities, etc.? This is what is known as the measurement problem in quantum mechanics. And I'm not exaggerating when I say that story I just told you is what we teach our students. And if the students have these questions, we tell them to shut up. I don't think this is a good policy. I think we should be able to do better than that. Because of these questions, which go under the rubric of the measurement problem, we have a whole field of intellectual endeavor called interpretations of quantum mechanics. Okay? There was never any field of intellectual endeavor called interpretations of classical mechanics. You knew what classical mechanics was about. There were particles, or there were waves, they were moving, you could predict them, etc. But this need, this apparent need in quantum mechanics to make measurement something special is baffling to us. And it's not just that it rubs us the wrong way. There's plenty of examples in physics where you're surprised by what nature teaches you, and you have to learn to adapt. The problem is these questions should have answers. The true once-and-for-all formulation of the best theory we have of the nature of reality should be a little bit more precise and clear and unambiguous than what we teach our students when we teach them quantum mechanics. So we would like to do better. You might think that in that circumstance, since quantum mechanics is the foundational theory for all of modern physics, you might think that the quest to understand quantum mechanics at a deep level would be recognized as one of the most important things we could possibly do in physics. The people who devoted their lives to these would be academic superstars. You would have different universities trying to steal them away with high-priced packages and salaries and so forth, and it would be the highest prestige occupation you could have in physics. Sadly, no, that is not what we do. It is the opposite of that. We have adopted a strategy of denial, where if you are a physicist and you think hard about answering these questions, you are labeled not a physicist, or a physicist who is too old to do important work anymore, and you're sent off to retirement. For example, there's a quote which is true from Richard Feynman, my predecessor at Caltech. My claim to fame at Caltech is that I sit at Richard Feynman's old desk. And people ask me why I got Richard Feynman's old desk, and the answer is it goes to the most senior theoretical physicist at Caltech who does not deserve a brand new desk when they move there. And Feynman said many things. He's a very quotable physicist, and one of his quotes is, "I think I can safely say that nobody understands quantum mechanics." Now, this is true if what we mean by this is nobody has an understanding that all the other physicists agree is right. Okay, some physicists think they understand quantum mechanics, but their friends don't agree with them, okay? Now, this is fine as far as it goes, but here's the problem. Rather than the rest of the community saying, no one understands quantum mechanics, therefore we better devote our resources to doing so, we say, nobody understands quantum mechanics, and they never will, and that's okay. This is what I think is a terrible embarrassment for the field of physics. I think we need to do better. It's kind of like the old fable, right? Aesop's fable about the fox and the grapes. Do you know this one? The fox sees the grapes, and he says, oh yeah, good, juicy grapes, I want to get them. Hops up and down, tries to get the grapes, but can't reach them. So the fox decides, you know what, I didn't want those grapes anyway. They were probably sour. So in case the metaphor is not clear, the fox represents physicists, and the grapes represent understanding quantum mechanics, okay? In the first few years after Schrödinger's equation and so forth, we did try hard to understand quantum mechanics. The giants of the field, Einstein, Bohr, etc. They didn't succeed to the satisfaction of anybody else, and therefore, for whatever reason, the lore became you shouldn't try. There was even a memo sent around by the editor of the Physical Review Journal saying that if anyone sends in a paper on the foundations of quantum mechanics, you should reject it without reading it. When I recently applied for grant money, I was told that if I want to talk about my research in cosmology and particle physics, that's good. If I want to talk about my research in the foundations of quantum mechanics, I shouldn't. Don't include it. Don't let anyone know you're doing that. You might get in trouble. I think we should do better. I think we can do better. Let's see what doing better might look like. You've seen this one, right? Schrödinger's cat. Okay. There's an experiment that was invented by Erwin Schrödinger, and it's important to understand why it was invented. Schrödinger, like many of the pioneers of quantum mechanics, his invention went far beyond what he expected. Okay, so he invented the wave function and Schrödinger's equation, but it had implications he didn't like. Schrödinger, like Einstein, was convinced that this whole measurement problem business was completely crazy. So the implication of Schrödinger's equation, the existence of a wave function, is that if we have different possible measurement outcomes, Before we look at the system is in a superposition of all the possible measurement outcomes. So what Schrödinger did was he invented this thought experiment to take that idea of a superposition of different possibilities and amplify it until it was macroscopically real. So the setup is you have a Geiger counter, and that's important because there's a little radiative source, a little bit of radioactive material that has a certain probability of emitting a particle, and that's a quantum mechanically uncertain event. That's what Schrödinger's equation does. It predicts what that probability is. And in the thought experiment, when the Geiger counter clicks, a hammer falls, it breaks a vial of cyanide poison. This is all in a box with a cat. The cat was alive, but if the vial breaks and the poison gets out, then the cat dies, okay? Personally, I see no reason to kill the cat, so I would like to replace the cyanide with sleeping gas. We can talk about an awake cat and an asleep cat, rather than a alive cat or a dead cat. Erwin Schrödinger's daughter, Ruth, actually said, "I think my father just didn't like cats." We don't have to be that way about the cats. So the point is that what Schrödinger was trying to illustrate is that according to classical mechanics, it might very well be the case that you have a box with a cat in it and you don't know whether the cat is awake or asleep. You can just have a lack of knowledge. But there's still a reality. There still is a single answer, even if you don't know. Even if you would describe what's in the box as a 50% chance of a cat being awake, a 50% chance of the cat being asleep, there is a truth to it. And quantum mechanics says something very different. Quantum mechanics says that after this experimental setup has gone forward, the cat itself is in a superposition of being awake and being asleep. Now, what is the lesson we're supposed to draw from that? Schrödinger says the lesson is, surely you don't believe that macroscopic objects like cats can be in superpositions of being awake and asleep in two different positions, okay? So he thought that this was a reductio ab absurdum, that something had to happen in quantum mechanics. He wasn't sure what it was, but like Einstein, he thought that quantum mechanics was incomplete as a theory of reality. Despite the fact that Schrödinger didn't like cats anymore, this thought experiment is really very helpful in sharpening your quantum mechanical intuition. So if the world is truly quantum mechanical, we should change our view of what is obvious and what is surprising. So if we're a classical person, we might say to ourselves, cats, as I've ever seen them, are either awake or asleep. They're never in a superposition of both. But, and this is exactly what Schrödinger is thinking, according to the laws of quantum mechanics, after that experiment, the cat truly is in a superposition of both awake and asleep. That's weird, I don't get it. Okay, that was Schrödinger's point of view. I would like to suggest that there's a different intuition you should have if you've truly absorbed the lessons of quantum mechanics, which is the following. Of course, cats can be in arbitrary superpositions. Everything in the universe can be in arbitrary superpositions. This idea of objects having positions and velocities and so forth is just a relic of our pre-existing classical intuition. What is weird, what is surprising, what is hard to understand is that when you open the box, you never see a cat in a superposition. That's what's weird. The cat being in a superposition is just the rules of quantum mechanics. That makes perfect sense. The weird thing is that when you observe the cat, you only ever see it in one or the other, either awake or asleep. What can possibly be going on? And people have been driven in the early days of quantum mechanics to suggest maybe there really was something special about conscious perceptions. Maybe the human mind really changed reality by interacting with it. We don't have to think that anymore. This is an old, out-of-date way of thinking. We can do much better than that, and that's what I want to tell you about. So here is what the textbook Copenhagen version of quantum mechanics would say about Schrödinger's cat. It says that there is a quantum system, in this case the cat, but there's a separate classical world where you and I are in. According to the Copenhagen version of quantum mechanics, you and I are not quantum mechanical. We really obey the rules of classical mechanics. It's not just a mistake. The tiny little microscopic system, or in this case the cat, might be quantum mechanical, but there's also a big classical world. And these two worlds can interact with each other. So you might have a state of the universe where the cat's in a superposition and there's an observer who's about to open the box. When the observer opens the box and looks inside, the wave function of the cat collapses, and you will either see the cat awake or the cat asleep. There was a combination of both, but then one of them disappears quickly and miraculously and instantaneously, and we're left with the other one. This is what we teach our students. And you see what the problem is, right? What if I just peek into the box? You know, like what if there was a fly that went into the box? There's a million questions that this perspective does not answer. It doesn't feel like the fundamental way that nature works in a very deep way. How can we fix it? Well, remember that before we added all these weird rules about measurements and observation, if we just had the wave function and Schrödinger's equation, quantum mechanics looked a lot like classical mechanics. There was a state of the system, it evolved according to an equation, and it would evolve deterministically forever. It was only when we added in the weird rules about measurements and observation that things got hairy. So let's try the following thought experiment. Let's erase all of those rules. Let's imagine that there simply is a wave function, and everything is quantum mechanical. Not only the cat and the Geiger counter and the radioactive substance, but you and me. Let's imagine that everything obeys the rules of quantum mechanics, and the rules of quantum mechanics are you obey Schrödinger's equation, and that's it. What would happen? What's the worst that can happen? Let's ask ourselves. It can get pretty bad, is the answer. So what if there were no such thing as wave functions collapsing? What if there was just the smooth, deterministic evolution of the Schrödinger equation? So rather than a classical world with observers in it, and a quantum world with atoms and cats and so forth, everything is quantum mechanical. But remember, I said there's a wave function for a particle or a cat and so forth. There's a little bit of a subtlety here. One of the rules of quantum mechanics is that there are not separate wave functions for every electron or every cat or every particle in the universe. There is only one wave function for the entire universe. So when you have different possible things, different possible positions an electron could be in, or different possible sleep or awake states of a cat, all of those are described simultaneously by a single wave function that says, what is the probability that the universe looks that way if we look at the whole universe all at once? Okay? This leads to something called entanglement, namely that the state of one part of the universe can be related to the state of another part. So when we start in this quantum mechanical story, the cat is all by itself. It has its own wave function, its own quantum state, superposition of awake and asleep. We, the observers, have not yet opened the box, so we are just in a unique state. We're wondering what we're going to see when we're in the box. Now you open the box, and all you have to go on is Schrödinger's equation. All you have are the laws of physics. There's no mystical, spooky collapse of the wave function. So you simply interact physically with what's inside. You see the light coming off, you feel, you put your hand in there and touch the cat. Whatever it is you're going to do, it's just the laws of physics. And according to those laws of physics, and here's where you have to hold on to your hats, you become entangled with the cat. So rather than the cat either being awake or asleep when you open the box, and the other possibility disappearing probabilistically and instantly, you smoothly evolve into a state where, just as before there was a superposition of cat awake and cat asleep, now there is a superposition of cat awake and you saw the cat awake, with cat asleep and you saw the cat asleep. That's what the Schrödinger equation predicts will happen. There's a superposition of both of these possibilities at once. Now, it should be clear why, back in the 1920s, the founders of quantum mechanics did not really take this possibility seriously. Namely that it doesn't ever feel like we're in a superposition, right? When we open the box, when we measure the spin of a particle or do some Geiger counter experiment, the Schrödinger equation all by itself says that we move into a superposition, but it doesn't feel that way. This sort of bare version of quantum mechanics, this most pure and austere version of quantum mechanics that just has the Schrödinger equation, seems to be contradicted by our experience, because it predicts things that we don't feel or experience ourselves, right? But there's a subtlety. Here's where things become kind of fun. I just told you that there's only one wave function for the entire universe. There's not a separate wave function for the cat and you, etc. That's where entanglement can come from. So in this superposition on the bottom, there's no possibility that the cat was awake but you think you saw it asleep, right? That's not part of the wave function of the universe. So if it's true that there's only one wave function of the universe, then we shouldn't simply include you and the cat. We should include everything. We should include the whole universe. So we call that the environment. Literally everything other than what we care about, we simply call the environment. So in that box with the cat, there are photons, right? There's light bouncing around inside the box. There are atoms of air bouncing around, and we don't observe them when we open the box. They're part of the environment. So let's imagine doing a slightly more careful version of our experiment. We start with the cat in a superposition. We have everything else in the universe, and then we have ourselves. We haven't yet opened the box. But this process called decoherence is simply the fact that, for all intents and purposes, the environment has been interacting with the cat all along, right? If the cat is asleep on the floor of the box or awake and climbing around, the photons and the atoms in the air will interact differently with the cat. So the first thing that happens, even before we open the box, is that the cat becomes entangled with the environment. That already happens, and then we open the box and we do our measurement, and then we become entangled with both, okay? So by the time we see the cat, by the time we get into the superposition that we had never really felt, the cat has already become entangled with the rest of its environment. Now this means something very, very profound. Once that happens, once the cat has already become entangled with its environment, it can never become unentangled. It's very much like mixing cream and coffee together, okay? An increase of entropy over time. It is what we call an irreversible process. You notice that if you look carefully, the environment states are different if they are entangled with the awake cat or asleep cat. They're very, very different from each other. There's no overlap. There's no relationship. So these two parts of the wave function, the one describing an awake cat, the one describing an asleep cat, will never interact with each other for the rest of eternity. They have split. They have gone their own way, okay? So, for all intents and purposes, it is as if they have become two separate worlds. There is a you that sees the cat awake, and there is a you that sees the cat asleep, and these two versions of you can never talk to each other. They can never compare notes. They are the same as the version of me that hopped to the right and the version of me that hopped to the left. This decoherence process, this fact that the cat or whatever, or you or your Geiger counter, becomes entangled with the environment, and that's an irreversible process, branches the wave function into two copies of the world. Both branches describe everything we know about in slightly different configurations, and once that branching happens, it never unhappens. So the bottom line is, what I've described to you is pure quantum mechanics. I didn't put anything in. I just used the ingredients that were already there. States, wave functions, the Schrödinger equation, and so forth. I simply asked the question, what would happen if I let the Schrödinger equation go and watched what happened as the system evolved according to those laws of physics? There was no collapse. I didn't need to define what I meant by measurement because measurement was just another physical interaction. I was looking at photons. All I did was obey the laws of physics. What naturally happens is that the wave function of the universe branches into different parts that are non-interacting with each other and describe different worlds. So this is what we call the many worlds interpretation of quantum mechanics. What I've been trying to emphasize is that at no point did we put new worlds in. Okay? The worlds were already there. If you think back to what happened in the Copenhagen textbook version of the Schrödinger cat experiment, we had to erase part of the wave function. If you saw the cat awake, you erase the part where the cat was asleep and vice versa. The many worlds interpretation of quantum mechanics is based on the fact that you are quantum mechanical just like everything else. If an electron can be in a superposition of that place and that place, then a cat can be in a superposition of awake and asleep, and then you can be in a superposition of seeing the cat awake and seeing the cat asleep, and the universe can be in a superposition of one where you saw the cat awake and one where you saw the cat asleep. This is automatic in quantum mechanics unless you get rid of it. So as one physicist said, it's not that many worlds is a theory of extra worlds. It's that every other interpretation of a quantum mechanics is a disappearing worlds interpretation. Once you do quantum mechanics at all, the world is already there. All the different worlds are already there. So this was invented by a graduate student, Hugh Everett, a graduate student of John Wheeler's in the 1950s. He fought very hard against his advisor, John Wheeler, in writing the PhD thesis because Wheeler's mentor was Niels Bohr, the boss of the Copenhagen interpretation of quantum mechanics. And Wheeler didn't really want to admit that his student had a better theory than Bohr did. So Wheeler kept pretending that they were actually compatible with each other, whereas Everett knew exactly what he was talking about, and he's like, no, the Copenhagen interpretation is a philosophical monstrosity, he called it, and we can do better than that. All we have to believe in is what quantum mechanics is trying to tell us. And what quantum mechanics is trying to tell us is there's no classical realm. There's no separate world of classical people making observations of quantum systems. You and I are made of atoms, which are made of elementary particles, which obey the rules of quantum mechanics. Therefore, you and I should obey the rules of quantum mechanics. That's how it should be. Everett's great insight is that taking quantum mechanics and the wave function seriously lets you come up with a theory that does account for the world that we observe. It is not in contradiction with our experience, but what it implies is that there are all these separate copies of reality. These other copies of the world still exist. People don't like that. Okay, you may know, you may have heard of this. People object to the idea that I could hop one way, hop the other way, and there's literally two copies of me, okay? So there are what I call silly objections to the many worlds interpretation of quantum mechanics. The first one is, and this is, I think, really the main one that people get hung up on, that's too many universes, right? All these universes. I mean, how often does it happen that the universe branches in two? It's not that it branches in two every time you make a decision, okay? So like, I literally had to push the button on my iPhone to send a signal so a photon could go down a beam splitter. That branched the universe in two. It's when a quantum mechanical system in a superposition becomes entangled with its environment and decoheres. That's when the universe branches. If you don't know whether to order pizza or curry for dinner tonight, and you finally make a decision, that doesn't mean there's another universe in which you order the other one, unless you use the phone to do a quantum random number generator, okay? Decisions in your head are purely classical processes. Most of your thoughts have nothing to do with quantum mechanics. But there still are a lot of worlds. It's very often that a little nucleus in an atom decays. Okay? Every time a nucleus decays or doesn't decay, that branches the wave function of the universe. Every time particles scatter off of each other in some quantum mechanically interesting way and then become entangled with their environment, that branches the wave function of the universe. So the answer is there are many branches of the wave function that might actually come into existence. You can calculate how many we're allowed to have before we run into trouble. The space of all possible wave functions is called Hilbert space. It's very, very big. Just like, a plane, a two-dimensional plane is two-dimensional. You can go in two different directions. Space that we live in is three-dimensional, up, down, left, right, forward, backward. We think that Hilbert space for our observable universe is about 10 to the 122 dimensional. That's very big. We're not going to run out of room in Hilbert space for all these different wave functions describing many, many worlds. Our intuition is not up to the task. But the math says it's there. And the math says it's there in every version of quantum mechanics. There are other competing versions that are still much better than Copenhagen. None of them say that there's no such thing as a wave function. That is crucial to quantum mechanics. And once you believe in wave functions, you can believe that the universe can be in superpositions. Another, what I think, incorrect objection is that this idea cannot be tested, right? It's important in science that we not just have good ideas, but that we compare these important ideas to data. Right? That we experimentally probe our ideas. And people say, you've invented all these new worlds, how do you ever test that idea? The response to that is, I didn't invent any new worlds. I just took quantum mechanics seriously. The entirety of the assumptions that go into the many worlds theory is there are wave functions and they obey the Schrodinger equation. That's it. Everything else is a consequence of prediction and implication of those assumptions. And are those assumptions testable? Hell yes, they are. Of course they are. Whenever we do a quantum mechanical experiment, we're implicitly testing the many worlds interpretation. If you want to falsify the many worlds interpretation, remember that the prediction of many worlds is wave functions don't collapse. They never do. They appear to collapse because of decoherence. So you and I get the appearance of a wave function collapsing, but it never really happens. If you were able to observe a wave function collapsing without decoherence, without becoming entangled with the environment, that would be evidence that many worlds is wrong. And there are versions of quantum mechanics where that's exactly what happens, and it's experimentally testable. So many worlds has implications that can't be tested. That's what really bothers people. There are other worlds out there, according to this theory, and you can't get there. You can't see them. In principle, you could see them, just like in principle, your cream and coffee could unmix from each other. In practice, that's never going to happen in the real world. But that's also okay. Every theory of physics has some predictions that can't be tested. That's not what matters. What matters is, are there some predictions that can be tested? And for many worlds, that's certainly the case. So I get a little frustrated by the public discussion of the many worlds interpretation of quantum mechanics because a lot of people object to it for the wrong reasons, which is frustrating because there are good reasons to object to it. I think it's true. I would personally say there's about a 90% chance that the many worlds interpretation of quantum mechanics is the right one, but there are perfectly rational reasons to be worried about it. It's not a fully developed theory yet. We haven't completely finished the task of matching many worlds onto what we see in the experimental world. I would much rather see the public discussion of the theory center on these reasonable questions for many worlds. So let me just give you a very brief introduction to what physicists and philosophers are talking about at the cutting edge of this task we have, this program of mapping many worlds interpretation onto the world that we see. One question is probability. Okay, I said that the rule that we teach our undergraduates in the Copenhagen version of quantum mechanics is the probability of getting a certain experimental outcome, a certain measurable result, is given by the wave function squared. And in the Copenhagen version, you basically treat that as a law of nature, as a separate postulate of the theory. There's something fundamentally stochastic and random about how nature works. In the Everett version, in many worlds, there is nothing random about the world. Everything is completely deterministic. The Schrödinger equation always applies, and the Schrödinger equation simply says what will happen next with 100% probability. But here's the problem. When you do experiments, you see probabilities. When you have in front of you a nucleus that you know is going to decay, we have no way of predicting with certainty when that decay will happen. The best we can do is probability, right? So there's a challenge to many worlds. How do you get probabilities out of a theory that has no probabilities in it? The other question, which I think is very interesting, is how does the classical world emerge? Again, this is not a problem for Copenhagen because in the Copenhagen formulation of quantum mechanics, the classical world is there. It's part of your assumptions. You're a big classical observer measuring little quantum things. In Everett, everything is quantum. So when Schrödinger invented the Schrödinger equation, he had an ambition. Remember, de Broglie said, well, maybe what we think of as particles, little electrons, are actually waves. And Schrödinger invented an equation that those waves would obey. But what he hoped would be that if you solved that equation for an electron moving around an atom, the electron would its wave function would squeeze into a point, and you would basically see a point moving around the atom. Sadly for Schrödinger, that's not what happens. Electrons spread out all throughout the atom. If anyone ever tells you atoms are mostly empty space, that is nonsense. That is not true. Atoms are mostly wave function. So the question is, why when we look at the world, when we look at the floor and the table and things around us, why do they seem to have positions? Why do they seem to be localized in space? How do you extract that classical reality out of the quantum mechanical wave function? So both of these questions are really good ones, okay? We don't know the once and for all final answer. We're working on it. I think that we do have really good suggestions as to where the final answers will come from. So let me tell you about that. This is a little bit of an intro to the cutting edge of research in this field. So for probabilities, here's the problem. Remember, we have a version of the laws of physics, which is just the Schrödinger equation. It's completely deterministic. Wave functions smoothly evolve. We know exactly what the future wave function is going to be. But we also know that those wave functions describe branching of the universe into multiple copies. So the way that probability comes in is that, among other things, you branch, right? I branched when I did the hopping left and right. There will necessarily be a short period of time when the branching has already happened. There are two copies of me, two future selves, okay? And neither one of them knows which branch they're on. This is called self-locating uncertainty. You know everything there is to know about the wave function of the universe, about the entire state of reality, but you don't know where you are within it. We can see this happening. Remember, when we started with the cat, the environment, and the observer, by the way, you now know is Hugh Everett, who also, by the way, left physics after he got his PhD because he didn't want to take the guff that he was getting. I mean, Wheeler actually sent him to Copenhagen to try to talk to Niels Bohr and the other Copenhagen people, and it was a disaster. It did not go well. So the story that we told was one where before you, the observer, know the answer to your question, which branch of the wave function am I on, the branching has already happened. This process of decoherence in which the cat or the quantum system interacts with this environment is incredibly fast. Numbers like 10 to the minus 20 seconds get thrown around, okay? So no matter how quickly you open the box and look at it, decoherence has happened much before your conscious mind can process the outcome of that particular experiment. And therefore, you always reach a stage that is similar to what we've pictured here, where the wave function is already branched. There are now two copies of you, but those two copies are identical. So you could imagine talking to those two copies and saying, well, which branch of the wave function do you think you're on? It turns out to be there's a process. There's a correct way of rationally assigning the probability that you're on one branch of the wave function versus another one, and what it works out to be is that it's the wave function squared. If the amplitude of the wave function for the cat being asleep was the square root of 30%, then you should give yourself a 30% chance of being on the branch of the wave function where the cat is asleep, and vice versa. So it works out. The fact that the actual probability rule in quantum mechanics is the probability is the wave function squared is more or less exactly what you would expect if the many worlds interpretation were true. It is not put in as a separate assumption. This is one of the reasons why the Everett interpretation or the many worlds interpretation is actually simpler and more compact than the Copenhagen interpretation or anything else. You don't put in things like the probability rule as extra assumptions, you derive them from the formalism. Now the other one, the classical world, this is where I really get excited. I wish I could talk to you about this for longer, but this is very interesting because we're beginning to understand a way of thinking about the emergence of space-time itself from the rules of quantum mechanics. You may have heard that one of the problems with quantum mechanics is that we can't yet make it compatible with gravity, right? Einstein invented his general theory of relativity back in 1915. He says that what we think of as gravity is really the curvature of space-time. Isaac Newton would have told you that space and time are fixed and absolute. Einstein tells you that space and time themselves are dynamical. They can change, they can warp, they can move around. This is only one of the four forces of nature that we know about, right? Particle physicists know about electromagnetism, the weak nuclear force, the strong nuclear force, and gravity. The other three forces, electromagnetism, strong, and weak, all have perfectly good quantum mechanical theories behind them. We do not have a perfectly good quantum mechanical theory for gravity quite yet, okay? So, when you dig into it, however, what you realize is that when we say we don't have a good quantum mechanical theory of gravity, what we really mean is we don't have a complete quantum mechanical theory of gravity. When you get to the extremes where gravity is extremely strong, at the center of a black hole or at the beginning of the universe with the Big Bang, that's what we don't know how to describe quantum mechanically. When we have a relatively benign situation, like here in this room where things fall down if you drop them because of gravity, there we can describe that particular weak force of gravity in perfectly quantum mechanical terms. So here is a way that we can try to make sense of how to do that. Remember, I told you about this phenomenon of entanglement, right? The quantum state of two different pieces of reality can be entangled with each other so that if you know something about one, you know something about the other. there's a typical way of thinking about entanglement that goes back to Einstein, of all people. In 1935, he wrote a paper called the EPR paper, Einstein, Podolsky, and Rosen. And he was just like Schrödinger with his cat, Einstein was trying to make you worry about quantum mechanics. He said, I can have two particles. They can both be spinning, right? Electrons have an intrinsic spin, so when you measure them, they're either spinning clockwise or spinning counterclockwise. And Einstein said if I have two electrons, because of entanglement, they can be in a state where either they're both spinning clockwise or they're both spinning counterclockwise. There's no possibility that one is spinning clockwise and the other is spinning counterclockwise. That's what entanglement says. But if I ask you, what will I observe when I look at one particle, the answer is I have no idea. It's a 50-50 chance. It could be clockwise or counterclockwise. All I know is that the other one is the same. So Einstein says, take one of those particles and send them to Alpha Centauri. Put them in a rocket ship. Send them light years away. Okay? And then I observe my particle here. I see, oh, it's clockwise. Instantly, according to the conventional rules of quantum mechanics, the other particle is clockwise also. So Einstein said, this is spooky. This is the origin of the phrase spooky action at a distance. How does the particle far away know that the universe is, that we got the result we did for this particle? A many worlds person says, well, when you observe this particle, the universe branched its wave function, and it branches it all over, and that's not very mysterious. But the point is that this amount of entanglement between the two particles doesn't depend on how far away the particles are, okay? I'm telling you this because if you've heard a little bit about quantum mechanics, you may have heard that. But there's an additional fact that these days our best theories of the universe are not theories of particles, they're theories of fields. There's the electric field, the magnetic field, the gravitational field, even the particles that you know about. Neutrinos, electrons, quarks, etc. These are all based on fields. And what a particle is a vibration in the field. There's many different fields all throughout this room. They're all gently vibrating. If it's vibrating very softly, we don't see anything. If it's vibrating enough, you see a particle there. Those are the rules of quantum field theory. So, while it is true that two particles can be separated by an enormous distance and still be just as entangled as they ever were, even in empty space, even in between the particles, there are still quantum mechanical field degrees of freedom, as we call them. There's still little vibrating quantum fields, even in empty space. And these are also entangled, and they're entangled in a way that it really does matter how far away they are. Namely, if they're nearby, if you take a region right here and right there, the two vibrating fields are very highly entangled with each other. Whereas if you take two spots very, very far away, they're very unentangled. They're not really related to each other, so that makes sense to us. At least, this is how we conventionally think about quantum field theory. Fields are highly entangled when they're nearby, not that entangled when they're far away. So here is the fun suggestion that I could make. What if we invert that? The statement I just made assumes that you know what you mean by nearby and far away, right? Because we're working in a classical space-time where we have rods and clocks and we can measure things. What if we didn't have that? What if we really were truly quantum, nothing but a wave function? What we have are different quantum mechanical degrees of freedom that are entangled or not. So what if you say to yourself, when the degrees of freedom are highly entangled, we will define that to be nearby, and when they are unentangled, we will define that to be far away. In other words, you get an emergent notion of geometry, of distances and times, out of the quantum mechanical properties of entanglement. So in other words, well, it's a long story, but here's the punchline. It works. It seems to work. Best we can say right now. Rather than starting with space-time, this is a new, exciting perspective on the problem of quantum gravity. Whenever we try in the conventional way of doing things to come up with a quantum mechanical theory of something, let's say electromagnetism, we start with the classical theory and we quantize it. The classical theory of electromagnetism was given to us by Maxwell and Faraday and others in the 1800s. There are rules for, if you have a classical theory, converting it into a quantum mechanical theory, quantization. But presumably nature doesn't work that way. Nature doesn't start with a classical theory, then quantize it. Nature just is quantum from the start. So maybe the reason why it's been so difficult to quantize gravity is that we shouldn't be quantizing gravity. We shouldn't be starting with the classical theory of general relativity and applying rules to turn it into a quantum theory. Maybe we should be starting with quantum mechanics. Maybe what we should be doing is not quantizing gravity, but finding gravity within quantum mechanics. And the first very tentative, very crude steps in this direction have been taken. And what we seem to find, under assumptions that seem reasonable, is that this emergent geometry that we define from quantum entanglement obeys an equation, just like anything should in a good, well-defined physical theory. And the equation it obeys is Einstein's equation for general relativity. Einstein's equation is the other equation I want to show you besides Schrödinger's. It's just as much fun, just as impenetrable to understand if you're not an expert. But it's not that conceptually hard. On the left-hand side, there's a expression which means how much curvature is there in space-time. And on the right-hand side, there's an expression which means how much stuff is there in the universe. How much energy, heat, momentum, and so forth. So this is Einstein's version of the gravitational field between two bodies depends on how far away they are, Newton's law of gravity, okay? This rule governs how the curvature of space-time responds to energy and momentum, and we're able to see that rule emerge from a theory that doesn't even have space-time in it, that has nothing but quantum entanglement. So it seems like maybe, if we're optimistic, cross our fingers, by taking the interpretational problems of quantum mechanics seriously, by thinking deeply about what it means to be a quantum state, how it evolves, branching, decoherence, etc., and asking questions about the emergence of the classical world in that theory, we not only get an answer that explains cats and electrons, but maybe the universe itself. Again, this is very tentative, new stuff. It might go away, but I think it's a good lesson for how new research directions can be driven by thinking deeply about the hardest problems. So to finish, let me give you a quote from Oxford physicist David Deutsch. He's a big promoter of Everettian or many worlds quantum mechanics. He says, despite the unrivaled empirical success of quantum theory, the very suggestion that it may be literally true as a description of nature is still greeted with cynicism, incomprehension, and even anger. What he means, of course, by quantum theory is the many worlds version of quantum theory without anything else, anything besides wave functions and the Schrödinger equation. That theory leads you to believe in a lot of stuff, including multiple branches of the wave function with as many copies of you, and you might not want to believe that. But after my talk, I hope at least that there is less incomprehension in the room. The cynicism and the anger are up to you. Thank you very much.
In the videos we've watched today, we've asked the question, what are the foundations of reality? What do you think the answer is? It's okay if you don't have an answer, but if you do, please leave a comment below. If you like this video, please do check our archive for more videos like this. We have one that we just put out on consciousness, and again, thank you for watching.